โลเทส
พี่ก๊อตได้ยินเราปะในฐานะที่เธออยู่ในซูมเป็นคนแรก
ได้ยินครับได้ยิน
โอเคขอบคุณค่ะ
ครับ
อ๋อก๊อตค่ะช่วยพูดอีกรอบหนึ่งได้ไหมจะได้เช็คว่าในห้องประชุมได้ยินไหมคะ
ได้ยินครับ
โอเคค่ะขอบคุณมากค่ะปิดได้เลย
ครับ
So you can use free Wi-Fi using this username and password. Oh, only 5 available now. First come, first serve.
Yes
โอเคค่ะทดสอบค่ะ ในซูมได้ยินเสียงไหมคะ
ได้ยินครับ
โอเคค่ะ ขอบคุณค่ะ ขอเวลาอีกสักครู่นะคะ
Good morning, everyone. I would like to welcome you all to the seminar on molecular dynamic simulations. Firstly, I would like to roughly about our schedule. We will start the seminar on around 8:50, and then we'll have a coffee break on 10:30. After that, we will have a lunch break on 11:45. And then the session will end on 4:40. I hope everyone has a great experience today and gain much knowledge as you can. Firstly, I would like to invite Professor Sirama to opening the seminar for today.
Okay. Good morning. Welcome to Chiang Mai for those friends from foreign country from overseas. So actually, Dr. Domani, who is the director of the Thailand Center of Excellence in Physics, to be here and welcome all of you, but she is unfortunately unable to attend due to her overseas schedules. So anyway, on behalf of her, we are honored to welcome all participants to the International Seminar on Molecular Dynamic Simulations for Organic and Inorganic Systems, taking place over the next 2 years at here, Chiang Mai University. And I would like to express our thanks to Rickent, to the Nishina Center for Accelerator-Based Science, to the Material Science Research Center at Chiang Mai University, and also to the Hub of Talent on Particle Accelerators. Okay. They are the one that co-hosting these seminars, and with the support from the Japan Society of the Promotion of Science Call-to-Call programs. I would also like to thank the Department of Chemistry, Chiang Mai University, for the venue of this seminar. The molecular dynamic simulation are the significant tool at the intersection of theoretical physics, material science, and computational chemistry. As the complexity of scientific grows, so does need for advanced MD methodology integrated with quantum mechanics, machine learning, and hybrid simulation approach. This seminar brings together experts from various institutes across Asia to explore a wide range of topics, such as MD in muon science and hydrogen dynamics, part integrals, and hybrid multicolor methods, ionic liquids, and biomolecular flexibilities, MD-MLDFT integration for battery materials and energy systems, QMMM simulations of organic interfaces. We are deeply appreciated by all speakers, participants, and committee's members, especially to Dr. Isao Watanabe from Nishina Center for Accelerator-Based Science, to Dr. Dongmani Wongratna Paisan, the Director of Thailand Center of Excellence in Physics, and Dr. Sakon Rimjam from the Department of Physics and Material Science, Chiang Mai University, for their leadership and contribution to this event. On these occasions, I would like to open the seminars on molecular dynamics simulations, which serves not only a platform for sharing knowledge, but also a catalyst for future collaborations. We wish everyone a successful, inspiring, and enjoyable experience. And again, welcome to Chiang Mai. Thank you.
So thank you, Professor Siramat, for the opening report. Now we would like to take a group photo of everyone first. Firstly, we would like to thank our chairperson, Dr. Isao Watanabe, for holding this seminar. Thank you very much for your contribution. Okay. Now we would like to take a group photo. Please, everyone, please come in front so we can take a picture together. Thank you, everyone. And before the meeting starts, so before the meeting start, I would like to inform all the speakers that since we have the conference online, we would like to use Zoom for the for sharing screen for the participant online. So here's the Zoom meeting ID that you can join. Please join before sharing screen and before beginning to speak. Thank you very much. So first one, I would like to invite Professor Watanabe for the first lecture.
Okay, so let's start the seminar now. So first of all, I'd like to thank you so much for all of the CMU, the staff members, to kindly arrange this opportunity for all of us. So then I'm very happy to come here again. And also, unfortunately, Professor Duamani is not here today. But I want to say my very appreciation to her, to owners, and also Tapani, everybody, thank you so much. So then what is the main purpose of the seminar is to discuss the MD simulation for many materials at this moment. So but the main purpose for my viewpoint, my main purpose of the seminar is just not only for presenting the from the speakers, but also sharing knowledge and discuss and find out collaborations among all of us. That is most important for me, because for my viewpoint, main reason to organize this seminar is I have my own research, the purpose. Then I want to MD performance to think about my own research. That is most important. Then I suggested to gather the many people, and also I would very interesting the Japanese researchers. Then I hope we could accelerate our own researches, including my research. Then to go ahead more and more, then to create the more publication. That is my main purpose. Okay, so then my talk is just 20 minutes, but I will be chair in the morning. So I said no discussion time for me. Okay, so if you want to talk with me, or question to me there during coffee time or lunch time, please come to me. Okay, so this is the main purpose of this seminar. So as I talk to you, my main purpose is to discuss muon science, how we can analyze the data taken by muon fine particle. So here is my old basement to work on a muon, Rutherford Upton laboratory in the UK. So here was my investment. So then the main purpose, how we can use muon. I have two main purposes to use MD simulation. One is for battery materials, another one is for DNA. So both are showing the charge particle motions. Within the battery material, ions are motioning. Within the DNA, we are now discussing the proton motion and electron motions. All are charged particle motions within the ambient temperature. So how we can discuss the MSRC result for those materials is my main question. The MSRC is very complicated, the techniques. So that if you write down the image of MSRC like that, however, I have no time. It's okay, very not so smooth. So we have no time to discuss this kind of the technical things, and I skip now. The image, how we can use the muon to sense the charge motion. This is just like an image. So charged particle, for instance, ions, that should have in magnetic spins. For instance, in a battery, lithium and sodium, they have the nuclear spin. And if that is motioning, muon, such kind of motion via magnetic interaction. So this is the image. Also same for DNA and proteins. So if the electrons and protons are passed through the molecules, so then we can. No, sorry. So please use this mic for all of the speakers. So then we can sense ionic motion or charged particle motion via muon. But the problem is we have two fundamental problems to discuss a muon result. One is we don't know where is muon, because muon is a fine particle. Of course, we cannot see, but we can handle, we can control. However, we cannot control the muon position inside the material. That is a fundamental question. So this is also the main research theme, even for MSR community in the world. So we are always discussing where is the muon, where is the muon. Then it's easy to kill the muon scientist. If you have a question, where's the muon? You can easily kill everybody. So then we have to, again, those kind of wonderful questions. Then we have some the computation methods. And another one is, the question is, muon is motioning or muon is just sitting inside the material. Also the question. So if muon is running around, the observation of the charged particle is just like a relative problem. But if the muon is sitting, it's very definite. Muon can sense easily the realistic ionic motions. However, we don't know whether muon is motioning or muon is sitting. So that is also the question. For instance, as you can image, in high temperatures, everything is motioning. Ions are motioning, the proton motioning. Of course, muon is motioning, running around through the material at high temperatures. So that means that we have to think about the temperature effect to discuss all of the muon result. However, it's quite new knowledge, so then we still don't know how we can estimate such kind of muon motion. That is in some sense very big fundamental problem, especially for DNA and also battery materials. So this is a very famous paper to apply the muon to the battery material done by Toyota company. So then I skipped the detailed explanation. So due to this, in the muon world, in the muon community in the world, the couple of people are now still studying the ionic motions inside the battery materials because the muon is a very fine particle. We can discuss ionic motion at atomic level. Very unique methodology. However, we have to discuss whether muon is running or not. So that is the reason why we need to think about MD, the simulations. So then in order to discuss the MD, but it's not so easy, honestly speaking, because muon is a very dilute particle within the material. That means that we have to discuss the muon effect as like a very dilute magnetic impurity. So as maybe computation people can understand, the dilute magnetic impurity problem is a quite heavy calculation. So for instance, this one is one of the existing supercomputers in University of Tokyo. So this is also very nice supercomputer system rather than our Likens one. So then, for instance, this is one example which has done by my researchers, my collaborator. So then we have to manage this kind of supercell. So quite huge amount of the atomic numbers we have to calculate at the one time. Then if we include MD effect, even using this kind of supercomputer, it's quite hard to handle everything. So then how we can include the MD simulation into the realistic condition. Then we've got that one key, the word is machine learning technique. So today, after my talk, Dr. Nagai is going to talk about how we can use a machine learning technique with MD simulation, which is very new, very new. So then he's also developing this kind of new method. So if you're interested in him, please talk to him. Then we can do many things, hopefully. And the next, my research is DNA, how like a protons or electrons is passing through the DNA or protein. That is one question. So then we can do the mere experiment with the protein and DNA. However, after muon attaches the molecule, that is the next question. Then we can simulate such kind of molecular state. Of course, we cannot control the molecular state. So then this is the one my collaborator say result to optimize the structure. So then she is the Vandru Fadila from Malaysia. So she's going to talk about something. So then we can do this kind of simulation, optimization of structure, something, but this is at 0 Kelvin temperature. So then after we inject the muon, what's happened is molecular is motioning at the room temperature. Of course, we have to think about this. Then how muon is attaching to the molecular. How we can discuss the muon result, MSR result. That is one problem. So then these days, we simulated the MD with the classical MD result. So my student is going to talk about this result today as well. So then how we can discuss this kind of structure. So it's one question. Then muon attached to those state as a molecule. So for instance, this is one result. Honestly, the MD result is like that. So molecular structure is changing by changing in time. That means that once muon stopped in the molecule, the muon state should be changing in time at high temperatures. So how do we discuss this? Then I try to discuss the average structure by using experimental technique. This is done by Rutherford Upton Laboratory. So then we measured the average molecular structure. But still, we need more discussion, more experiment to discuss the molecular structure, to discuss the MD result. So everything is ongoing. That is why I want to discuss with all of you how we can solve that. For instance, if the mu attached to the molecule like that, so at a room temperature or high temperatures, muon is motioning as well with molecule. So expansion and rotation, easy we can understand. There are some motion or modes. However, muon is additional particle to the molecule. So then we have to discuss how we can include the, this kind of additional particle into the MD simulation. As long as discussed with a couple of people, all three MD people said, no, impossible. So then I have to break such kind of conditions. So then I found the possibility to use a PMID method. So Dr. Shiga is going to talk about this kind of new technique so that we can discuss the muon motion in here. So the many new things is going on at this moment. Then I start to try to find out more answers with many people as much as possible. Then Dr. Nagai came to the Malaysia to discuss the possibility of how to use his machine learning technique. And then this is my first visit to the Chiang Mai. Just I found the Professor Pialat. So she's also very strong, the MD professor. Then I want to have more talks and collaboration. Banajan also very strong. Then if possible, I want to talk with all of you together to find out the clear answer for muon science. Then I'd like to come back to the research themes with all of you. That is my hope. That is my wish. So of course, my wish, my plan is just a part of this seminar. A part of this seminar, okay? So could you please discuss with all of you, among all of you, then find out the more people. So that then I selected the very wonderful people there to discuss how we can catch up the important information from those people. Then could you please, especially for students, could you please talk to them as much as don't hesitate. They catch up the researchers and discuss at any time. We are very willing to. So especially those two, the Japanese one, would give you the very new knowledge and techniques to discuss MD simulation. So thank you so much. So then please enjoy discussions and communication today. Then as I talk to you, no discussion time for me. So the next speaker, I'd like to invite next speaker, Dr. Shiga, from JEA. He's going to talk about the PMI method, how we can use that one for MD simulation.
One moment, please. So thank you so much for inviting me to this very nice conference. I'm Motoyuki Shiga from JEA, and my talk is about path integral molecular dynamics of hydrogen in materials. And before my talk, I would like to just briefly introduce myself. My interest is in the development of ab initio molecular dynamics. And I started this topic when I was in, in my school days. So I finished my PhD in Tokyo Institute of Technology in 1999. And then I became a principal researcher in JEA, which I work on. And so I will, yeah, I'm just continuing this research topic from that for a very long time. So my office is in this Kashiwa, which is a suburb of Tokyo, just few tens of kilometers north of Tokyo. And this is my office, which is inside the campus of University of Tokyo. So this is talk about this nuclear quantum effects, which is not which is often neglected in conventional MD simulations. But for light atoms like hydrogen, they exist, and even at ambient temperature, and reflect major physical properties. And as you can see in the water spectrum, the thermal energy is 200 wave numbers, which is very low compared to many of the vibrational degrees of freedom in water. So that's why there could be a chance that these nuclear quantum effects play a role in this hydrogen in materials. And for example, a typical example is isotope effects on thermodynamics properties, because in classical statistics, we obtain all these properties like energies, free energies, entropies, and derivatives of free energies that are all mass independent, which means that we do not have any difference between, for instance, H2O and D2O. But in reality, we do have difference. For instance, the freezing point or the melting point or the boiling point different between H2O and D2O. So these can be only explained when quantum effects are turned on. So how do we include nuclear quantum effects? There are many methods, but I use a method so-called path integral molecular dynamics. And here we use a trick that in which the quantum statistical of a particle is equivalent to classical statistical replicating particles, which is called beats in this case. And for instance, if we just want to describe the wave function of or the density of the diatomic molecule, it looks like this in the left, but in the path integral representation, we can re-express this density by replicated particles. So this path integral techniques is very common, and I just want to introduce Nawi. I discovered that he's working on this many years ago, and this is about this asymmetric hydrogen bonding in double hydrogen bonded system. You can see that in this system, we do see very strong effects on the OH bonding bond lengths in this system, which is because of this the 0-point effects and the tunneling. Okay, so in order to make this PIMD easy, we have been developing a code called PIMD, which stands for Path Integral Molecular Dynamics. But so in this case, we run ab initio calculations for electronic structures for many structures at the same time, and collect those data to update the structures, and then we run the simulations over and over again. This type of simulation is not only used in path integrals, but also many kinds of simulations like the free energy calculations and non-adiabatic effects and so on. So this is all implemented in this software, and this is open source, so that everyone can use. So this is very now he has worked already on this molecules and molecular clusters. I'm working basically on the condensed matter. So basically it's hydrogen in materials with periodic boundary conditions. And this is a typical example of liquid water. So you can if you do this with ab initio MD, which is now routine work for many of you. This is depicted in the left-hand side. If you turn on the quantum effects, it looks like this in the right-hand side. You can see that these many particles replicated, many particle hydrogen, which represents the beats. And if you do that, you are able to reproduce experimental results for the distribution functions. Quite nice, as you can see in this slide. These oxygen, hydrogen, and oxygen-hydrogen radio distributions are in green, is very consistent with the neutron scattering experiments. So we can do that. Now we can also kind of go step forward in order to compute other physical properties. This is a very basic one again for the pKa of water, so the acidity. So in order to do that, we must obtain the free energy in order to auto-ionize this the water molecule. So what we do is control the coordination number of our water molecule. We pick a water molecule and rip it off, rip the one proton off the molecule, and as we do that, we compute the free energy cost to do so. So as we here I depicted the free energy integration over this OH bond length, and as you can see, the free energies differs very strongly. Sorry. Oops. What? Okay. Sorry. Strongly with respect to the nuclear quantum effects, and so sorry for the interruption. So in the experiments, you can see that the pKa of H2O are different, which is consistent with this result. Okay, so I can go on and on to do many more things. This is high pressure ice, and you can see that there is phase transition of the proton as you compress the ice from phase 8 to 10. There is a symmetrization of the proton structure, and this structure is dependent on the nuclear quantum effects. And this one is another example of hydrogen on metal surface. And as you can see here, the hydrogen distribution, the hydrogen is on the adsorbed on the surface, and it has some distributions on the surface sites, and the distributions are very different when you take care of the nuclear quantum effects. So as you can see, the difference between the classical and quantum distributions, they are very completely different after quantum effects is considered. Now we can do compute the diffusion constants of hydrogen in metals in this case, using the same technique I have introduced for pKa calculations. Basically, I compute the free energy profile as I move the centroid of the particle, of the hydrogen particle, along the reaction coordinate describing the diffusion in these methods. As you can see, the barrier heights are very dependent on temperature, whereas this is nearly a constant in classical case. So this is because of there are two effects. There are this 0-point effects of vibrations and tunneling, and actually in this case these effects compete with each other to realize the diffusion coefficients. And as you can see, compared to the classical case transition state theory, the quantum transition state theory is better in agreement with experiments with respect to the temperature dependent diffusion coefficients. So now I move on to so this is this was done with initial on-of-fly calculations with brute force kind of simulations, but we can now use neural network potentials that mimics the ab initio calculations, which will be talked about after this by Professor Nagai. And briefly, you can reproduce these density functional theory in this case. So they are in line with these in energies in all of these structures, as you can see from this graph. So using this, we can speed up the simulations. We can speed up the simulations, and this is how it looks like for this hydrogen diffusion in palladium. And as you can see, the hydrogen is diffusing along the reaction coordinates in the interstitial region of the metal atoms, and it goes back and forth so that it recovers this recrossing effects. Then you can really reproduce maybe you realized in the last slide I showed you that the diffusion coefficients is a little bit overestimate the experimental values at high temperatures for the transition state theory. But here, as we include this recrossing effects directly from MD simulations, we really recover this correct this overestimation to get really on top of our experimental values, as you can see. This as you can see in this figure, compared with experiments. So this is another one with in BCC metals, this niobium, hydrogen diffusion in niobium metal, and the hollow symbols are experiments, and the solid symbols are simulations for H, D, and T with different colors, black, red, and blue. And as the species is lighter, you you see this tunneling, and you can see that this the diffusion coefficients is higher, larger as for lighter species, and this is almost perfectly consistent with experiments. Okay, so I'm now working on refined parallel algorithm for PIMD in order to speed up the simulations. And this was done very recently, and I won't go into the details, but for path integral simulations, we were able to speed up like well, 10 or 100 times than before, which made it possible to run simulations at the nanosecond level, which was not possible before. And this is in this case, we try to reproduce the key capacity of liquid water. And as you can see, in both cases with different functionals of DFT, this experiment is in this black line, and you can see that this ab initio or the machine learning MD overestimates this heat capacity badly, but if you turn on the quantum effects again, it is much more consistent to experiments. And in this case, we needed a nanosecond time scale PIMD in order to converge our results. Okay, so for now, we have introduced this path integral simulations mainly on this statistical averages, but we can also extend this idea to approximate quantum dynamics. And there are many methods up to now, and the representative methods are centroid, it's called centroid MD and ring polar MD simulations. But there are problems in these methods, and I will not go into the details, but there are the research on this direction is going on. So I tried to refine these methods recently in order to cope with the vibrational spectra of hydrogen materials, and one of them is called this Brownian chain molecular dynamics, which is the extension of path integral simulations to dynamics, approximate quantum dynamics for mainly for spectrum. And basically, we try to gather information of dynamical information out of this ring polymer object, trajectory of this ring polymer. And of course, in path integrals, we don't have basically the dynamical information, but the basic idea is that we can approximate this correlation function out of path integral simulation. The so-called Kubo transform quantum correlation function by the trajectory of this ring polymer. And there are these the physical properties that is met from this method, and also from this BCMD technique that I've just mentioned. And here's one example from this method, and you can see that the black dots are the peaks from the IS spectrum of this in this case this is ice, high pressure ice, and the peak position is now corrected by this method. And as you can see, there is a redshift of this OH peak because of the nuclear quantum effects. Because because of the harmonicity in this OH stretch, and as well as all this HOH bending peaks. So, and then we are trying to reproduce this neutron scattering in inelastic neutron scattering spectra, and yeah, so in this case also there are strong nuclear quantum effects, as you can compare the results with classical MD, and in this case there is a different nuclear quantum effects than this water ice, in the sense that the peaks, the vibrational peaks are blue shifted with respect to the quantum effects. So there are many other things I have been working on, but I will just mention what I have been working on recently. This is not necessarily the nuclear quantum effects, but I'm working on this the X-ray explosion spectra or aqueous solutions, biomass conversion at water metal interface. This is more of ambitious electron structure calculations. And then I started doing muons, and this is MUSR of muonated ice, and in collaboration with Dr. Nai, I'm also working on this quasi-crystal. So maybe he will talk about this. Before I close my talk, I just want to mention on the ongoing work on muons, and this is amorphous ice, the muon particle in amorphous ice, and as you can see, the part in blue is this muon particle, and this looks like you know, if you know this system, it's very close to this Zundel structure, and but of course it's a muon, so it's not exactly the same, but it's very close. So using this structure, I can the experimental my colleague has done these experiments, and it looks very consistent, and so I'm happy to. I hope this is a very long-standing collaboration, so I hope this will be published soon. So I would like to acknowledge my collaborators, including Dr. Nagai in University of Tokyo, and all other people who worked with me, and especially Bo Thompson, who is in our group, and he's developing the PIB code and running the simulations. Just a takeaway. This is nothing to do with my work, but maybe just to mention that there is a conference called International Conference for Molecular Simulations, and this was started in Japan in 1994, occasionally, but then after 2016, it is held every 3 years. And the last one it was in Taipei in 2023, and it is planned in October 2026 in Bangalore in India. And the number of participants is around 300 to 500. And the participants is mainly, of course, they are from Europe and United States as well, but mainly this is organized in Asia. So if you are interested, go to this site and maybe contact this person who is taking care of the next conference. Yeah, so this is it. So I will take any questions. Thank you very much.
Thank you so much for the time just answer. Any questions? Please.
Thank you very much for sharing your interesting result. And actually, in Chiang Mai University, we have a setup of experiment together with the simulation, as we discussed yesterday. One of it is actually about the amorphous ice as well, because we try to simulate reproduce the astrochemistry, setup in that room. Yeah. And one of the measurement we try to find out is to characterize, for example, down to terahertz frequency of vibration from cluster model of amorphous ice structure. And we found that it's quite hard to just use the typical quantum calculation to get the accurate frequency. Yeah. So for your so from your expertise, could you please suggest? Yeah. So which is better? For example, try with the part integral MD or the machine learn or the ANN. Yeah. Could you please suggest? Thank you.
So in order to reproduce this vibrational spectra, of course, you need to have two effects. So you consider this the potential is accurate enough in order to describe the potential energy surface of your system. So basically, you need the quality of ab initio quality. Of course, but you don't need to. Of course, if you can fit this to machine learning potentials, it's better because then you can collect the statistical average better, right? Because with machine learning potentials, it's much faster, right? The calculation much faster. And then you can add the nuclear quantum effects on top of that. So basically, what I was showing is that we can use machine learning potentials for path integral simulations, and that will be the best one if you can do that. Yes.
Okay, any others?
Very nice talk, Dr. Shiga. I'm from Malaysia, so basically, I'm very interested to study immune effect on proteins and DNA and stuff like that. So you mentioned you use the machine learning potential to do that. May I know what kind of information we need to feed in order to come up with the potential, and so that we can prepare for DNA or like proteins?
Yeah, so that's a very challenging part of machine learning potentials. Right now, maybe yeah, Dr. Nagoi will answer that question. But right now we have these the machine learning potential. So the machine learning potential became popular in 2007 after this York Beta has developed so-called neural network, high dimensional neural potentials. And there, the problem is was and now is that it is useful for systems that contain very few amount of elements like the if you think of this kind of metal hydrogen metals, you have only two elements, right? So in that case, it's very, very useful, right? And then you have another branch of machine learning potentials, which takes care of molecules. And there are many methods developed very recently that that takes care of polymers and these things. But as far as my feeling is that we are going forward to more complex systems like yours, but we're not still there yet. I would say, but maybe in few years, the situation will change very quickly. So this is very this research area is very active. So maybe I will change my opinion tomorrow. So I don't know. Yeah.
Thank you so much. Sorry, the time is rushing up. So could you please catch him up during coffee time, lunchtime? Okay, so let's move on to the next speaker, the Dr. Nagai from University of Tokyo.
Okay. So can you hear me? Okay. Thank you for coming. I'd like to thank the organizers for giving me an opportunity to talk here in Thailand. This is first visit to Thailand. Okay, so I'm studying in the Information Technology Center of the University of Tokyo. And I'm also studying in the Department of Advanced Material Sciences. So now I can have the graduate student. So this is a drawing. Before talking about my research, I would like to introduce the chance for you to use supercomputers in Japan. And also I'd like to show the chance for you to study in the University of Tokyo in Japan. Okay. And in this talk, I'd like to talk about the machine learning method. in molecular dynamics. First of all, I'd like to introduce me. I was born in Hokkaido, which is a northern island in Japan, which means that it snows. So this is completely different from here, okay? But I think there are also similar things. I mean that in this area, Hokkaido area, there are good seafood. So in Thailand, it's many seafood. So I really want to have some seafood. But unfortunately, I realized that in Chiang Mai, there are mountains. So there's no sea. But yeah, in Thailand, last night I really enjoyed the seafood and also khao soi, which is a local noodle. Yeah, I really enjoyed that. Okay, anyway, I got PhD in the University of Tokyo, and now I'm an associate professor in the University of Tokyo, and I'm studying the condensed matter theory, superconductivity, material science, and also machine learning and physics. So before talking about my research, I'd like to show the chance for you to use supercomputers in Japan. And in Japan, there are 8 oldest national universities which have own supercomputers. And now we have a JHPCN, which is the infrastructure for researchers to use supercomputers for free. So if your proposal is accepted, you can use supercomputers in Japan. So, and I'd like to say that you can access the computational resources, which is equivalent to the $20,000 for free, if your proposal is accepted. The condition is I mean that if you have a collaborator in Japan, you can use supercomputers in Thailand or other countries. And now I am a member of the JHPCN Administrative Office. So if you have a question about this infrastructure, please ask me. Okay, and I'd like to show the supercomputers, spec of the supercomputers. The University of Tokyo has 2 supercomputers, Wisteria and Miyabi. Miyabi is a new one. This was built in this year. And Miyabi has NVIDIA Grace Hopper 2000 superchip. And this price is about, I think, $40,000 per node. And now Miyabi has 1,120 nodes. Okay, so this is huge supercomputers. And if your proposal is accepted, you can use this supercomputer here or other countries. And we also encourage international joint research projects. So we can cover travel expenses from Japan to somewhere or from somewhere to Japan. Of course, the budget is limited, but you can have a chance to go to Japan or collaborate with Japanese researchers. And the important date is usually 6th January, but this is old schedule because the schedule is not fixed. But this is a deadline for application. So there is a time now, I think, now only July. So you can find researchers in Japan. So if you want to collaborate with Japanese researchers, please feel free to contact me because I'm studying the Information Technology Center. So which means that there are many computational science researchers, and we can how to say, introduce someone in your field. And I'd like to introduce the studies in University of Tokyo. And there are several, of course, there are many projects in the University of Tokyo. This one is for undergraduate students at overseas universities. And this project will not provide any financial support. So if you have some budget in Thailand or other countries, you can go to Japan and you can study in the University of Tokyo. And you can choose me. And also, of course, there is some budget project. I mean that scholarship and housing are provided by this program. So if you are interested in, please see the this website. This is for a short-term program for undergraduate students. Also, I'd like to find PhD candidates in the University of Tokyo. And of course, there are many scholarship programs in the University of Tokyo. So if you are interested in studying in the University of Tokyo, please see the website or please contact me. Okay. Anyway, I would like to introduce my research. I'm interested in the speed up with machine learning. in field of machine learning, there are of course many applications now, image recognition, AI chat like ChatGPT. But I think that the important point is that we do not have a theory of these. For example, if you want to distinguish whether there is a cat in a picture, of course we can, if we gather data, or I mean that pictures, then you can distinguish there is a cat or not. But we do not have a theory to distinguish the cat or not. But you can build a machine to imitate the theory. But in simulations, we know the theory. So in the simulation, of course, we want to use the machine learning technique. So how to use that? And for example, the A is the input. For example, the position of atoms in the molecular dynamics, and the output is B. B is, for example, energy, or I don't say space heat, or then another. There are many physical observables. Then usually we use molecular dynamics or density function theory ab initio calculations. But sometimes this computational cost is very heavy. So we want to avoid this computational cost. So now we imitate this heavy computational calculation by replacing by using the effective model constructed by the neural networks. Then we have a speed up in the molecular dynamics simulations or other systems. So I'd like to show, I'd like to explain the machine learning molecular dynamics. As you know, everything is constructed by atoms, of course. Virus, DNA, materials, humans, animal, Earth, and galaxy. But I think last year some cosmic researchers say that cosmic ray is not constructed by atoms. But anyway, on the Earth, everything is constructed by atoms. So if you can simulate atomic motions, you can simulate or predict everything on the Earth, I think. But the important point is that computational cost is very heavy. So we cannot simulate everything, of course. But if you can do that, it is very useful. For example, if you find the new batteries, sometimes what kind of atoms is good for good ion conductivity. So now we introduce the machine learning model to do the machine learning molecular dynamics. Then it takes 1,000 times faster. I mean that, for example, if you have some candidates, 10 candidates for new batteries, then, for example, it takes 3 years per one candidate. This means that 1,000 days. But if you use the machine learning model, this means that it takes 1 day per one candidate. So this is very fast. And also, if you use the supercomputers, you can easily put the jobs to the supercomputers, for example, 10 or 100 candidates. Then after 1 day, you can have 100 results. Then this means that we can easily find the candidates of the new materials. So it is very effective and useful. So I'd like to show the example of the machine learning molecular dynamics. This is quartz crystals, and Dr. Dan Histman won the Nobel Prize in 2011 for discovery of the quartz crystals. But the important point is that this is very complex systems. For example, in this case, 4,352 atoms. And also, this is, sorry, I cannot see the atoms. So these are many atoms. But the important point is that this is 30,000 atoms, but you can simulate this in the molecular dynamics. And the accuracy is, of course, very important. And the accuracy is is very similar to the ab initio calculation. So it is very useful. Okay, now I'd like to talk about my research. I mean, self-learning Monte Carlo. This which is machine learning techniques in molecular dynamics. And I'd like to show the problems in machine learning molecular dynamics. And in machine learning field, we have to gather data. Data is very important to construct the effective model. But in the molecular dynamics, this is difficult sometimes because atoms are located in the continuous space. This means that the possible data, a number of the possible data is infinity. So this means that which systems are better to train. We have to gather many data, but the number of the candidate is infinity. So we have to choose the structures. And the other problems is that how do we conclude that the number of the trained data is enough in your simulations? For example, if we have 1,000 data, but we don't know this is enough or not, Also, we can have 10,000 or 100,000 data, but before doing the simulation, we do not know whether this is enough number or not. So this is a big problem. Okay. If your potential is not well trained, the atomic structure is broken in long-time molecular dynamics simulation with use of machine learning potential. For example, in this case, and this one is, I think, I don't know the number, but you can see that the crystal structure is completely broken. So we want to avoid this system. So now I'd like to introduce my method. So important point is that we don't know the definition of the not well trained. So how to conclude it? So now we want to make a method which can do robust molecular dynamics also, and we want to have a good training method. So now we introduce the self-learning Monte Carlo method. I think it's not familiar with this in molecular dynamics field, so I'd like to explain the Monte Carlo method. In molecular dynamics, usually we calculate physical observable with integrating something like this. This is based on the statistical mechanics. So we calculate time averages in molecular dynamics. But we can calculate this value with using Monte Carlo method. Monte Carlo method is integration method. So we do the importance sampling. Then we can calculate the physical observable. So this means I would like to say that molecular dynamics and Monte Carlo have same result. So you can use Monte Carlo method to get some physical observable in molecular dynamics field. So now I'd like to introduce the new method with use of the Monte Carlo method. So this is a self-learning hybrid Monte Carlo method, SLHMC, and procedure is as follows. Usually, if you use the machine learning MD, just do the just calculate the forces and do the calculate the movement of the atoms. But in this method, SLHMC, we put the original calculation here. A green circle means that original calculations. So first, we calculate the energy of the original model. Then we do the machine learning MD to move atoms. Then we do the we calculate the energy of original model. So and so on and so on, we can get the physical observable because green circle means the Monte Carlo process, and we move the atoms in the machine learning MD. So this is the self-learning hybrid Monte Carlo method. The important point is that accuracy is equivalent to the original calculation, not effective calculations, because we do the original calculation on the green circles here. And the important point is that we also gather data, training data at this point. This means that during a simulation, same simulation, we can get data. Then this means that we can train the effective model. So a new machine learning model is obtained during in the same simulations. So then we use the new machine learning potential in this here. I mean, that's the right line or the right line. And we can improve the effective model in the same simulations. This means that if you do the Accelerator-Based simulations, then you can improve machine learning potential effectively. And finally, you can get the converged machine learning potential. So this is very effective. In many machine learning methods, usually we gather data for training, and we train the data, of course, and to get the effective model. And then we do the simulation for evaluate the effective model. But sometimes it is not good, so then we gather more data. But in self-learning Monte Carlo method, we do 3 steps in same simulations. This means that we can get converged machine learning potential, and we can get the physical observables in same simulations. Of course, there are various kinds of molecular simulations. The first principle MD, this is so-called ab initio MD. Of course, the accuracy is very high, but computation cost is very high. And if you use the machine learning molecular dynamics, it is very fast. As I said, it takes 1,000 faster. But accuracy is not exact compared to the first principle molecular dynamics. But with the use of the self-learning hybrid Monte Carlo method, the accuracy is completely equivalent to that of the first principle molecular dynamics. Because as I said, the molecular dynamics and the Monte Carlo is same. I mean, that has the same result. But computational cost is middle because we have to put the original calculation in the simulations. So there are two ways to use the self-learning hybrid Monte Carlo method. One is you want to do simulation with exact accuracy in the ab initio level in the system. Or if you want to construct accurate effective model for machine learning molecular dynamics, it is better to use self-learning Monte Carlo. And this is a Monte Carlo method. This means that there are many applications in various kinds of fields. For example, spin system, electrons, atoms, molecules, and or also lattice QCD. Lattice QCD is a high energy theory for the quarks and gluons. So I mean that I would like to say that there are many applications. And I'd like to show the examples. First one is on-the-fly training. We, for example, consider the alpha quartz, SiO2, and this is a horizontal axis is the number of the that first principle calculations, and the vertical axis means that accuracy. So every 100 step, we train the effective model. Then we can have the converged machine learning potential. And also, as I said, this method is accurate compared to I mean, the accurate fit is equivalent to that of the first principle calculations. So this means that this is a radial distribution function, and we can see that the result is completely same. And also, we can speed up the simulations. And this is MSD, mean square displacement, and this becomes a constant if the system is solid. So we have to, and this horizontal axis is the number of the DFT calculations. And if you increase the length of the molecular dynamics, you can reduce the computational cost to calculate these kinds of things. And I would like to show the stable long-time molecular dynamics. And this is the yttrium nickel boron carbide. As Professor Dr. Shiga said that there are 5 elements, which means that this is very difficult sometimes. But with the use of the SLHMC, we can get good machine learning potential. So we use this potential to in the molecular dynamics simulations without SLHMC. So we can clearly show that there is some temperature dependence of the photon density of state or other physical quantities. And the important point is the calculation time. And left figure, this is for the SiO2 case, and left of left is the original calculations, and the vertical axis is elapsed time. So which means that it takes 800 hours. But with the use of SLHMC, it takes, I think, 30 hours with the use of the 200 CPU cores. And in the case of the yttrium nickel boron carbide, we just do the molecular dynamics with the effective converged potential. But in this case, with the use of DFT original calculations, elapsed time is about 800 hours. But with the use of the SLHMC plus molecular dynamics, machine learning molecular dynamics, it takes only 30 hours. So it is very fast. And I'd like to show the liquid silica. I mean that liquid. We developed the SLHMC for NPT ensemble. NPT means that constant number of the particle and constant pressure and constant temperature. In this case, we know that sometimes the MLMD simulation is unstable because we have to change the unit cell in the constant pressure case. So after 550 picosecond at 4,000 Kelvin, and in the case of the machine learning molecular dynamics, it is broken like this. But with the use of SLHMC, we can have the correct structures because we reject the structures. Because this is Monte Carlo step, so this means that we have some accept-reject step. So if the structure is completely different from the physical structures, we reject the sample. We reject the structure automatically. So we can get the stable simulations. So, for example, we compare the original molecular dynamics simulation. I mean that aberration molecular dynamics. This is consistent with the original one, and also we can calculate the long time simulations. Then we can reach the long time diffusive region in these systems. And also we show the we calculate the structure factor, which is measurable in the X-ray experiment. This is a comparison with experiments and theory, and we can have the good agreement. So with the use of the Accelerator-MC, we can do the stable long-time simulation. And finally, I would like to show the recent works with Dr. Shiga. I would like to show the quartz crystals. I think it's not familiar. I think with I mean that this is a complicated material, and usually in solid system we have a crystal structure, usually fourfold, or I mean that usually if you have some crystal, and then we can have four-fold crystal like this, or like a salt in a shell. But if you see the quartz crystal, this means that you can see that five-fold. This is very beautiful, I think. And this means that this is not crystal. I mean that there is no translational symmetry in the structure, but there is some structure. I mean some rule to make this structure. And we know that the quartz crystal can be described as a projection from higher dimensional periodic structures. For example, in this system, we can understand this structure with using a 6-dimensional space. So this is very difficult to think about this 6-dimensional space, but this crystal structure is a 3-dimensional projection from the 6-dimensional space, periodic space. So now we want to detect this kinds of high-dimensional property in experiments. In experiment, there is a good experiment, and as you might know, in solid there is a D'Hondt law. I think this is written in the statistical mechanics or condensed matter textbooks. And the important point is that if you have a solids, the specific heat becomes 3 kb because there are 3 kinetic energy terms and there are 3 vibration modes. But this 3 means that 3-dimensional space. So if you measure the specific heat, usually in higher temperatures, you can have 3 kb per atoms. But in quartz crystals, we can observe the 5 or 6 kb. This means that, okay, so solid is of course in the 3-dimensional, but 6 or 5 means that some high dimensional or 5-dimensional or 6-dimensional, we don't know. But in experiment, we can observe high specific heat. So there is a mystery. And this was, I think, discovered in 2001 or 4, I think 2001. So there is a 20 years mystery. So now we want to construct, I mean that we want to investigate this origin. Then with collaborated with experimental guy in the University of Tokyo, and they measure the specific heat and in aluminum, palladium, ruthenium quartz crystals, and we make the machine learning potential with use of Accelerator-MC. Because the aluminum, palladium, ruthenium system is very complicated like this. Then with using machine learning molecular dynamics simulations, we know the origin of this high value of the specific heat. Then we know that aluminum diffuses in the structures. So, and we can understand this diffusion is originating from the 6-dimensional property of the quartz crystals. So I'd like to summarize my talk. I'd like to introduce the self-learning hybrid Monte Carlo method, Accelerator-MC. There are 2 good things. One is the exact method. This means that the accuracy is equivalent to that of the ab initio calculations. And this is on-the-fly training method. So you can construct the effective converged machine learning model with use of Accelerator-MC. And these methods are already included in the PIMD. And this was developed by Dr. Siga. So you can use this SHMC method for free. Of course, because the PIMD is open source software, and the machine learning potential software is, I use the ANet. ANet is also open source software. So you can use this method for free, and you can use this method today, okay? And so I think it's very effective. Okay, this is the final slide. Thank you for attention.
Thank you so much. Any question or comments?
Thank you very much for your presentation. I'm metallurgist, so I've been working on aluminum alloys, and one of them got quartzite crystals. So that's come to my interest. Have you got any experimental data to support with this simulation also? Do you have any experimental data to support or to kind of validate the simulation as well?
Yeah, and I think there is some experiment to detect some fluctuation or diffusion of the aluminum atom, but it's very new experiment, so there is not so much data. So usually I use the simulations, and of course we measure the specific heat, yeah, which is indirect relation, I think. But yeah, but I think there's a paper.
Because I've now been working on I try to process or to make the high thermal stability aluminum alloys, and diffusion is the key at elevated temperature. And I think we can discuss more about this. Maybe we can do some work together. Okay.
Yeah, and he is the head of materials. It's a center. He have tons of material, I think. Okay, very interesting talk. And I have one question regarding to your developed method, the hybrid MC. In this case, you mentioned about the way that you can accelerate the simulation by cut off some candidate. Yeah, could you please elaborate more? How can you reject some structure? Is that from the spatial information or from energetic information? Could you elaborate more about this? All right, thank you.
We use the energy difference between the structures. If the energy is too high, this means that it's not physical. Yeah, so we reject it. Yeah.
So in this case, it means that we don't need to have the well-defined structure to simulate, right? Okay, thank you very much. This is very promising.
Any others? I have one comment. If the diffusion is the key, could you please investigate whether MSR investigation there or not on this material? So as I talk to you, the MSR should be a good tool to investigate the diffusion. Okay, any other from network, remote? Okay, nothing? Okay, thank you so much. So shall we move to the next speaker? Next speaker is Professor Pierlat from CMU.
Okay. Good morning. It's my pleasure to be here today, and I'm really glad to see you all again. Yeah, and in Chiang Mai. Yeah. For who is the first time in Chiang Mai, I hope you enjoy our scenery around, because the Chiang Mai University is just very close to the mountain, and we have fun fact is that our newbie each year we need to walk up to the mountain. Yeah, this is first task for the student, right? Okay, and for the talk I would like to deliver today, and actually I'm really happy that I learned from other lecture as well. It's about the factor governing molecular assembly that we have done here in CMU. As this workshop is mainly about the molecular dynamic simulation for organic and inorganic system, so I would like to introduce some of our research work regarding to this system. Right. And for Department of Chemistry, actually, we found as one of the first building and department in the university, and one of the first faculty as well. And we would like to serve all the research and also the culture and the environmentally conservation. Yeah, so all the aspects we try to work well together. And here our staff, you see, we have around 70 members in the department, just the Department of Chemistry, and around 15 is a physical chemist. And for me, I'm the principal investigator of computational and simulation modeling laboratory. And this lab actually firstly initiated by Professor Wanna, who now moved to UM. Oh, that work. Okay, thank you. That's work. Okay. Yeah. And so, yeah, this is our member. Our lab try to provide the computing service for the student and also to the researcher. So we work together with maybe across department, across faculty to do the simulation to answer their question. So the problem is somehow very complicated. As I mentioned before, sometimes we don't know what is the real information, which is um, the most reliable one, and we try our best to answer all the questions. And through this work, we also try to collaborate from with other university and from international, including Chiang and also UM. Yeah, and we learn a lot from our collaborators. Right, and our research going from the single crystal model compound of the polymer to study the hydrogen bond formation and the assembly of the structure. And also we expand the simulation from atomic level to mesoscopic level to simulate the soft matter in that way. And also we expand to the periodic system recently to the coordinated polymer lanthanide-based system to study the way that the material can act as the molecular sensing or carbon dioxide capture in such a way from their assembly structure and from its chemical properties. So recently, we deal with the enhanced catalysis of carbon dioxide cycloaddition reaction from using the single crystal of the structure that we can characterize here. For this case, we use the morph structure. And for the other study is about the supercapacitor model development, which based on the imidazolium ionic liquid as the electrolyte. And the fourth one is about the proton conductivity mechanism in supramolecular structure. And the last one I would like to introduce today is about the selective molecular recognition using the host gas chemistry. For the first case, the host structure in this case is the well-known Kirkwood uril, which have the imidazolium part in the structure. So it have both combination of the hydrophobic part and hydrophilic part that can interact with the gas structure. And this structure have the high potential to develop further for inclusion reaction and also for drug delivery application. In this case, so we start from this pumpkin-like structure, and we found that when we do the MD simulation of the structure using combination with three-dimensional reference interactive site model developed by Professor Norio Yoshida and Professor Hiroyuki Nakano, yeah, we found that we can find the correlation of the free energy observation related to the changing of size of the host structure or the CB structure in this systematic change. And also we can get the energy of binding with the host structure, which is with the gas structure, which is a small organic molecule in this case. And we can get the inline free energy result with the experimental result and also the Poisson-Boltzmann model, which is the state-of-the-art method for free energy calculation. We expand more to also the binary mixture solvation model. In this case, mainly work by my postdoc, Dr. Green, who is sitting here as well. Yeah. We studied the influence of water ethanol to the binding of gemcitabine, which is one of the drug for cancer. Yeah, and in this case, we found that by calculate the point chart using 3D rhythm self-consistent field, there's some systematic change of the host structure, the CB structure, as a function of the molar ratio of the solvent in this case. On the other hand, when we look at the gemcitabine, the small molecule that should interact with the host structure, the chart is quite stable in this case. But just this slightly change of the chart, we found that it can contribute to the change of the dynamic from MD simulation. For the host itself, it's not changed a lot, but for the gas structure, when it interacts in the complex, there's some transition which can be depicted from the RMSD plot in this case. When we look inside what happened, we found that at high water content, there's some slightly rotation of hydroxyl group of the gen side chain. But for the higher ethanol concentration, there's a rotation of pyrimidine membered ring during the binding. For the whole structure, it's actually not changed much, just slightly changed from the circular structure to the elliptical-like structure for the high ethanol concentration in this case. By combining this internal energy with the solvation energy, we found that we can get the trend of binding free energy, which in line with the experimental result, just around 6 kilocalorie per mole different, which is better than the previous calculated result by TDDFT calculation, but not the part integral MD. So I'm not quite sure, maybe it's too heavy. Yeah, right. But yeah, so in this case, we can get the improved result. Right. Also, we extend to the MOF structure or the coordination polymer structure in collaboration with Professor Pienpat, who is expert for the MOF synthesis here in Department of Chemistry. In this case, from the experimental result, we know that the design zinc to lanthanide 3 heterometric coordination polymer from their work structures just like this radar here, just like this. They can enhance the catalysis of carbon dioxide cycloaddition at ambient pressure. And we got that the result that with the change of the substrate epoxide, just slightly change the chain, the percent of conversion can be changed in this case. So we use the calculation to predict the possible binding for the substrate of interest, and we can get the trend of the change of the hardness with the experimental result. And at the moment, we explore more on the mechanism, what happened. But yeah, the result is just ongoing, so I'm not share today about this. And the other work mainly made by Mr. Michael, who also sitting here. My PhD student who also have a good chance to work at Ligang about muon simulation. For his work in CMU, mainly we work about the ionic liquid structure. Again, we interested in the imidazolium-like molecule. Actually, it's more from my interest. Because my previous work is about the nephron, the proton conducting thunder ion formation. But we have the limitation of resource, so we cannot do such a heavy computation here, right? And also at that time, I'm also interested in the imidazole structure. And in this case is imidazolium cation with the NTF2, which is a well-known ionic liquid, as it have the promising ionic conductivity and also solubility in many green chemistry. So it's one of the molecule of interest in our team. In this case, we like to study the molecular assembly of this particular ionic liquid both in the bulk structure with the mixed solvent as well. But the mixed solvent I would not discuss today because not finished yet as well. And some on the supercapacitor model, right? For the study with for the ionic liquid only, we do the calculation and also dynamic simulation and try to compare the result with the experimental team head by Professor Sakhon you met yesterday, who is the head of P-cell lab. In this P-cell lab, they try to design the equipment, the instrument to characterize, as I tell you, ranging from terahertz or free electron laser. Yeah, so they like to design a lot of equipment to investigate the interaction of various of material. In this case, so we try with the ionic liquid structure. And from the study, so we found that if we use only the isolate molecule system, the structure with the highest hydrogen bond formation seems to be the most stable. But when we change to the bulk structure by MD simulation, we found that it's more complicated in that case, and it's better. I mean, it's fit better to the spectrum, but not the best, not that really fit. Yeah, so that is why I asked the question in the previous talk by Professor Shika. Yeah, because we still try to figure out what happened. But what we found is that hydrogen bond interaction play important role in the structure assembly in this case. So it not only the cation anion, not only electrostatic interaction, but also the hydrogen bond information have the crucial role. And the highlight of the hydrogen bond formation is at the imidazolium, the hydrogen at the center, yeah, with the oxygen of sulfonium group, yeah, of NTF2. This evidence also found in the supercapacitor model. Actually, we start as we have the limited result at the first. So we start from the very small model first, only 50 ion pair, and then we expand better, right? Because now we try to dig more and more information. In this case, we found that the highlight of hydrogen bond formation also related to the phenomenon at the double layer formation at the interface of the electrode. In this case, when we apply the external voltage using potential bias, we found that the change of the hydrogen bond formation also change with the change of the bias of potential in this case. And we found that the arrangement or assembly of the structure can be deviated by applying the one you can see the change of like a random structure to the more in the pattern in this case. And we study more about the symmetric effect, yeah, but not just 3-dimensional, not 6-dimensional, right? Just this dimension, right? So we study further on the symmetric effect on this imidazolium-based ionic liquid. So we change from the ethyl group to methyl group, so it's become more symmetric. And just by this slightly change, we found that there's some deviation of the result. So what happened? We analyzed the surface charge evolution in this case, physical ion layer formation, local structure, and also the differential capacitance related to electric double layer model. Yeah, just slightly change from asymmetric to symmetric. We found that in the C1 MIM NTF2, it have less movement, less surface charge accumulation, and less responsive in this case from the MD simulation. And when we look at the differential capacitance profile, it changed. Yeah, it changed. And when we fit with the Goodwill Knopfscape model, we found that the packing efficiency changed 2 times. Yeah. So C2 MIM NTF2 have less packing at the surface. But in such a case, SC1 is very well packed. So it's still element intact at the surface, and resulting in the change of the differential capacitance model. And now we explore more on the differential length. Yeah. Right. Last but not least, so I would like to express my appreciation to our member at computational simulation and modeling laboratory. And also, I would like to express my appreciation to TAPE Center for inviting me today. And also, this research work cannot be complete without budget. So very important one. So I would like to thank all the funding agency, including Material Research Center. Yeah, thank you very much. Thank you for your kind attention.
Thank you. So any question or comments?
Yeah, thank you for your talk. I wonder, I mean, you regarding this ionic liquids, what kind of force fields are you using? Like,
So recently we changed to polarizable force field, but it's heavier, take longer, right? But yeah, so I wonder whether if we can get more accurate data, yeah, because still some deviation found from our results. So we kind of it's not that good fit. Yeah, so when I look at so we discussed about the possibility to use, for example, machine learning, MD simulation, or yeah. So I asked for your suggestion about this, right? Thai binding method. Oh, yeah. In this case, not yet. Too heavy for my system still. But if we can have, we can get more access to more results, then maybe we can try. Yeah, yeah. Maybe yeah. For example, application to computing resource. Thank you very much.
Any other question or comments? Nothing? Okay, so the time is rushing up. So turn a coffee break now. Thank you so much for speaker.
Thank you so much. So we're gonna have 15-minute breaks, but first, Professor Chayasit have something to share with the group. Just only take 5 minutes. So while we're waiting, I would like to inform that our breaks will serve downstairs. So you go downstairs and turn left and go straight. The breaking room is right on the corner. So I will take you there. Thank you.
I'm very sorry. May have just 5 minutes. Just want to introduce myself first. I'm Chayasit Panjongmasert. I'm the researcher, lecturer, and also the head of Material Science Research Center here in Chiang Mai University. Just a brief introduction of the center. The center itself focuses on material science, which you know that is interdisciplinary. And so we have more than 140 members. Okay. I try to share it again. Okay. Okay, it's okay now, right? Okay. So I'm Chayasit, head of Material Science Research Center. In the center, we have more than 140 members from Chiang Mai University from 10 different faculties: engineering, science, medicine, and other, and also 4 research institute in Chiang Mai University. So what I trying to say is that we work on the many fields in material science research, advanced material for medical aspect, green energy material for environmental concern, and innovative material for industry. And also people been working on simulation in material science application, in material application. And just want to show you, I think if you have time, you can go around this one. This is our new building, material research, material innovation building. So that from our research, we can transfer to the industry. And the last thing, because I have just 5 minutes, I just would like to advertise about the conference that we're going to have here in Chiang Mai. We've been working with the Department of Industrial Chemistry. It's going to be the broad subject of the materials research. And you can see one of the topic is computational material science. And if this is the first time you come to Chiang Mai, I hope this is going to be your second time. 1st to 4th December in Chiang Mai. And it's going to be this conference series. It's 19 already. And as you can see, we hosted it in 2015. So it's 10 years now. This year, December 1st to 4th December. I hope I'm going to see you all here again in Chiang Mai. Thank you. I just want to advertise about this conference. Thank you very much.
Thank you, Professor Chayasit, for advertising the conference. So now we're gonna have a short break. We'll be back here again in 15 minutes, so around 10:50. Yes. So now let's go have a break downstairs.
Kramer? So the SR, please.
Thank you very much. So my name is not typical Japanese, even so I'm working at Riken. I didn't prepare a slide, but I'm actually from Austria, which is in Europe. So we are the ones without the kangaroos. I studied, so my focus is a little bit different because I studied biotechnology and biochemistry, made a PhD in organic synthesis, and I'm now working on condensed matters, primarily lipids and carbohydrates, and I'm studying lipid-lipid and lipid-protein interactions using a combination of computational chemistry, experimental results, synthetic chemistry, and then verifying everything in biology to gain a better understanding of fundamental biological processes. And you can see in the background, this is Mount Fuji, which I could see every day nearly when I left my flat next to Riken, because in Riken you can see Mount Fuji. This is of course a nice zoom. So Mount Fuji is much further away. And because I'm from Austria, I love snow. So I like it with snow. But Riken doesn't have a facility in Hokkaido, so I have to stay in Tokyo. So today I want to talk a little bit about DFT calculation work that I've done to assess reactivity. And in the second part, I will talk about some of the molecular dynamic simulations, especially about lipid interactions. And interspersed will be the verification with experimental results. So you all know computational chemistry, so I don't need to go through it, but basically, if we do DFT or quantum mechanics simulations, we want to know something very precise on the small molecule. When we go for molecular dynamic simulations, we want to see a more larger picture of the system. So we have to choose our method depending on what we want to do to keep the cost reasonable. And in the end, we have to verify everything we calculate with the experiments, because I can calculate many things, but if my starting point is wrong, my result will be wrong. So I will talk today about one molecule primarily. This is called phosphatidylglucoside. This is a lipid consisting out of a glucose head group, a phosphate group, and then we have a glycerol with two alkyl chains. This was first found in 1970. It was proposed to be for bacteria, and in 2002, when I came to Japan, we identified it from mammalian sources. It's in the umbilical red blood cells. So we confirmed the structure, and we found that in natural compound, this stereo center here is not only R configured, but also S configured. So this is indication that the biosynthetic pathway is not a canonical biosynthetic pathway. The interesting part in general for me about the stereo center and the glycerol is, if we look at the origin of life, then in the pre-cell, in the first cell, both stereoisomers of the lipids existed. But at some point, the bacteria split off from the eukarya and the archaea, and the bacteria have only R configured lipids, right-handed. And at a later point, there was a split between eukarya and archaea, versus the archaea only got the left-handed and the eukarya got the right-handed. Eukarya domain is where the animals, the fungi, and the plants are located. So in this lipid that we have seen here is from the animal domain because it's human. But we still have a little bit of S formation. So this is therefore a non-canonical biosynthetic pathway, which has been, it doesn't, I don't know. Change screen. Please share. Yes. No, but which one do they see now? If they see this one, can you check? Is now okay? Okay. Hi. So, as I said, the non-canonical biosynthetic pathway is actually quite interesting. We sort of did a few years ago. It's an enzyme that is well known to transfer glucose onto other carbohydrates, making an alpha linkage. But if it has a phosphate group as an attached group, it will make a beta linkage. So this is an enzyme that can make two different types of linkages. It's a very old type of enzyme, actually, that can do this. But now I cannot go to the next slide. Down. No. Okay. So this phosphoglucoside, when we have the lipid interactions, the lipids like to separate, and we have one antibody that can stain this lipid, so we can visualize it. And this is a EM image of a cell surface on the outside, and every black dot is one of these lipids. This is a gold particle that is connected, and you can see that they are not homogeneously distributed. They are heterogeneously distributed on this membrane. And also, when we take a bigger picture, we can see that there are dot-like areas. The red one would be the phosphoglucoside. And this means that these lipids do not homogeneously distribute in the membrane between other lipids. This is known as lipid phase separation. And lipid phase separation is based on the physical principle that like. So it's not like electronic where you say that the plus and minus attract. Because in the nucleus of the atom, you have all the positive charges sticking together. They are all alike. If you would have plus and minus attract, then we would have always an electron and the proton together. But in physics, like. And the same way you can see it in the membrane, if we have lipids that are taller, for example, then they will start to stick together and form an area where they're sitting together, because then we can minimize the energy of the system, because the bad water interaction of the two long lipids will be minimized in this way. So the system will always try to go to minimal energy. And these kind of domains are called rafts. And if you look here, you can see they are sitting kind of together in certain areas which we then refer to as raft areas. The dimension of this raft is somewhere around 10 to 20, 30 nanometers. So it's like a few hundred lipids. The lipid itself is a neuronal guidance lipid. So during the development of the embryo, it allows neurons to go into certain areas of the spine only, and blocks neurons from going to other areas. And using this guidance method, we can have a biological assay, so that when we inject the lipid on one side, this is a neuron that develops and is moving and then sensing the environment on the growth cone here. And if we inject the guidance cue that is a chemorepulsive cue, it will move away from it, from the injection point. If it is a chemoattractant, it will go towards it. And if it is the non-active compound, it will just keep growing straight. So on the right side here, you can see the explanation, you can see the result. If you take our neurons, if we add this compound, 10 micromolar, and then it diffuses towards the growth cone, so we will end up with just a few molecules there. It will be sensed by the receptor, and then it repulses by about 10 degrees our cone to the side. So this will be the biological assay that we will use afterwards. Now, I want to talk about developing a covalent inhibitor for the sensor of this lipid. And covalent inhibitors means that you have something that binds into the enzyme and then will be attacked by a nucleophilic residue of the enzyme. So you need an electrophile here, and that will constantly bind this compound into the pocket. So you have a covalent bond formation, permanent inhibition. And the classical way is, for example, if you have any kind of esters, you have an amino group from a lysine attack the ester, it will connect the ester residue to your enzyme. You can also take activated sulfates. And we have synthesized a homologue of a phosphate, which is a squaric acid. And recently somebody used the squaric acid, which on one side is an amide, on the other side is a methoxide, it's an ester, amide ester compound, which is an active compound to link it to a protein. So we said, okay, we know that thioesters are better than esters, so we want to try a thioester analog of our compound. So then the enzyme would attack here and kick out the thiol side, and we would have a permanent inhibitor. But we know that in our receptor, there is an amino group that can make the attack. Now, in the previous paper where they used a similar squarate, they said that the thioester might not work well, because on the next slide. Because they think that the resonance structure would make an attack on a negatively charged carbon unlikely. Now, usually when we have thioesters in chemistry, we say the better leaving group, which is the thiol that has to go out, or the If this is an OH, it's an alcohol that goes out. The weaker base is the better leaving group. So the thiol should be the better leaving. So I thought I can use simple computational chemistry with model compounds to identify whether our thiol analog would be better or not. And for this one, I first thought about calculating, getting an idea of the molecular electrostatic potential. And particular for a chemist mind, if we can have point charges, it's the easiest to get atomic charge that we can see whether reactions can happen. But of course, we have to keep in mind that point charges are not true definitions of, I mean, this is not absolutely true. They are just abstractions because we don't know where the atom ends and we don't know how to distribute the electrons between the atoms if we have a bond, which is actually the biggest problem. So, but on the larger scale, it should still mimic our molecular electrostatic potential. Now, there are multiple ways to calculate atomic partial charges, these point charges, and the most common one is using the molecular charges. But it's well known that they are depending on your base pair. Because basically what happens in molecular charges is they just divide them half on each orbital, which is not anywhere close to correct. Natural bond orbitals, it's much better, but you need already a license because the implemented version Gaussian is only 3.0, I think, and now they are 12. So they are trying for publication 3.0 is not sufficient. But it should give you better results, and then you could also try the Q-time theories. But of course, they get more and more calculation expensive. So just to highlight the difference, this is in a simplified system. We just have a thioester versus an ester versus an amide. And if we look at the charge of this carbonyl carbon, in case of the simple system, the basis set doesn't make much change. It's a relatively small change only. But if we do the same calculations in the square rates, because we have a larger delocalized system, then we can already see on the right side, the green numbers, this carbon here has significant difference in its positive charge. I mean, in both cases, it's positive and not negative as the simple drawing of a resonance structure would suggest, which is a big difference. So this problem, if you draw this resonance structure here, this is not the end of the resonance structure, because you can make another resonance structure where you flip this negative charge down into the diagonal oxygen. And then you can get the oxygen minus and the N plus. And we know that when we have multiple resonance structures, not every resonance structure has equal probability, which simply means that this resonance structure, the negative charge here, is a low probability resonance structure. So it contributes very little to the real electronic distribution in the system. Just a reminder that nothing is really equal in the world. So in order to get a better idea about reactivity, the next thing was to consider quantimolecular orbitals, because the smaller my HOMO-LUMO gap is, so the gap between the attacking highest occupied molecular orbital versus the attack lowest unoccupied molecular orbital, the more likely the reaction will happen. And so smaller gap makes it better, more likely to react. Now, if you look on the left side, this is a ester versus a thioester model calculation. Then we can see if the amino group, a neutral amino group, so it would be just the pi orbital that attacks. If the free electron pair in the p orbital, then we can see that the LUMO of the thioester is lower than the LUMO of the ester. So it makes the thioester more reactive. but it's a very small difference. Roughly, this 5 electron volts HOMO-LUMO gap makes medium reactivity. So when we go to our square rate, the ester versus the thioester, then we can also see this reproduced. The thioester has a lower LUMO compared to our to the ester on the left side here. So the attack of the neutral amine to the thioester is likely more likely to happen. So it should have at least similar reactivity or slightly better reactivity. Now, in biology, thioesters are active esters because, for example, the coenzyme A, which is one of the important compounds in biology for esters, esterification is a thioester up here. And this is higher in energy. The thioester is higher in energy compared to an ester. So we have first, the fatty acid is converted into a phosphate ester, which is even higher in energy. And from there on, we just go down in energy towards our ester or amides in the proteins. So thioesters are active esters versus esters are non-active esters. But when we do the same calculation, we just compare the relative free energy of a square rate ester versus a thioester. We have about 5 kilocalories per mole lower, which is opposite to what we would expect from a normal ester. This is a question and also about the hydrolytic stability. So when we look at the simple free energy of reaction, this doesn't mean now that I analyze the activation energy. This is just the overall change in energy if you have a conversion of an ester with water into a free acid and an alcohol. So then we have to put roughly 2.3 kilocalories per mole of energy into the system. So esters easily form by themselves. Versus when you have a thioester, then the calculation would say you release 2.3 kilocalories per mole. And this is actually very well reproduced in experimental data already a long time ago. If we do the same calculations with the ester of the square rate, the hydrolysis, we can see we have a bit less energy released. If we have we need to put a bit less energy in when we want to break ester into the free ester. Versus we need to put 7 kilocalories per mole of energy into the system if we want to break our thioester, which is very close to this energy difference here. So the thioester is lower in energy than the ester, which makes this mixed square amide thioester more hydrolytically stable than the esters. And this is not unwelcome because if we want to use this as a medicine, we only want to have it react once it reaches the binding pocket, and not when you eat it already and it binds to your tongue. So we want hydrolytic stability. And the reason for this hydrolytic stability is when we compare a vinyl ether. So we have a double bond and then an oxygen, a bridged oxygen. The vinyl ether with the vinyl thioether. Well, in chemistry we call a thioether sulfide, but for the simplicity, I will call it here a thioether. Okay. Then a thioether is about 5 kilocalories per mole more stable than an ether. And this is also experimentally reproducible. So when we hydrolyze a vinyl ether, we release 7 kilocalories per mole. If we hydrolyze a vinyl thioether, we only release 2 kilocalories per mole, which means that the vinyl thioether is much more stable. And the reason it's more stable is simply because in the vinyl ether, the oxygen can donate electrons to the double bond. So the free electron pairs of the oxygen will delocalize here much stronger. Versus the sulfur is not able to donate its free electron pairs to the neighboring double bond. So we have a much more polarized environment. And if we look at the keto-enol tautomerism, we can see this same picture, because in the vinyl, so an enol state, compared to the aldehyde state, we have 9 kilocalories per mole lower energy for the aldehyde, and the double bond is on the oxygen. Versus in the sulfur case, the difference between the thiol and the ethanol thioal is only 0.5 kilocalories per mole, which means they're like a 1-to-1 ratio. And the combination in the squaric acid is we have an ester here because we have the carbonyl group on this side, which can coordinate. But at the same time, we have the double bond, which gives it the character of the vinyl thioether. So we have the stability of the vinyl thioether, but the reactivity of the ester. So if we look at the comparisons of the thioesters are much more energy rich and react easier, but in the squaric case, they have less energy. But our homo-lumo gap is smaller, so it makes it more likely to be attacked. So we have a hydrolytically more stable compound, likely that is still reactive in the enzyme is our conclusion. So we synthesize the analog with the thioester present, and then we tried a simple in vitro experiment, just keeping our thioester with the primary amine and incubate it over time at neutral pH. So this is our starting material peak here, and the left peak on number 13, this is the product peak as a reference. And after 0 hours, we have no product. But after 1 week, we have a very tiny amount of product formed. This is because the pKa of this amino group is around 9 to 10. So at a pH of 7, we have basically no NH2 present. It's all NH3 plus. Now, inside an enzyme, you have micro pHs, so your protonation will be very different. If we go to a pH of 9.1 in our buffer system, then we can see that within 24 hours, we can see the reaction start, and within 1 week, we have conversion. The nice thing is that even after 1 week, the thioester has not hydrolyzed. We just keep it at room temperature, and the ester is still stable, which means the compound is stable inside your body probably. So when we do our turning assays, which I have introduced before, this is our biological system. Now what we do is we add our compound, and then we see whether we can have a reaction. And when we add our compound, then we can see that it blocks the reaction. This is on the right side here. But so I have this is the better side. When we do a pulsed experiment, which means we have our neurons that we take out of the embryos, we grow them, and we add 10 microliter of the compound 1A, which is our thioester. We incubate for 4 hours. Then we wash everything, and we wait another 13 hours. So during these 4 hours, the thioester in the enzyme, in the receptor, should have reacted and made an inhibitor. And then we start our assay system, where we challenge the compounds that were incubated with our material with our usual guidance cues. And we see that we have no guidance reaction. So we have inhibited even 13 hours after application, which means the reaction worked as intended. If we use a different guidance cue, we can still see guidance because this works via different receptors. So because we have a good hydrolytical stability, we have a low reactivity, we will not react with any kind of amino group in there. We need to sit in the binding pocket long enough to just have a very selective reaction. So we think we have a very good balance between reactivity and stability in a thioester, much better than in an ester. So demonstrate high hydrolytic stability, high target selectivity. And just short a little bit about molecular dynamics simulation. In lipid chemistry or lipid biology, we use cyclodextrin, which is a carbohydrate, a cyclic carbohydrate, in order to solubilize lipid tail. And the question is always how many of the cyclodextrin molecules want to sit around the lipid tail? Is it 2 of them or is it only 1 of them? So we synthesize cyclodextrin that is deuterated so that it doesn't disturb our NMR signals. And I did the simulation for the cyclodextrin with 1 lipid in a 1-to-1 mixture in a water droplet over time. And then I just looked where the cyclodextrin is, of course, in the dynamics moving up and down. And we can have a statistical distribution that it is mainly around the carbon 10 where the whole cyclodextrin is sitting. And the head group is relatively far away. The difference between these points is whether the 6-8 position is downwards or it's upwards. It's just in 2 directions. If we do the same simulation with 2 cyclodextrins, then we have 4 possibilities of how they are oriented. We can see that they reach much closer to the glycerol and to the carbohydrate parts, because we also have here the glycerol to the phosphor interactions, and they're getting very close in certain combinations. And if we look at the NMR signals, when we demycelize in the micelle, lysophosphoryl and then we add our cyclodextrin so that we have it now solubilized, we get the sharp signals. And we can see that this signal here from 4.2 is shifting to 4.3 ppm. This has something to do with the shielding of the protons. So when we plot it, we can see a downfield shift, especially for the glycerol parts, and the slight upfield shift in the carbohydrate parts. And this strong downfield shift in the glycerol parts supports the notion that we actually have 2 cyclodextrins, because they need to be very close to shield the glycerols from the water interactions here. So at the moment, we think it's more consistent that you have 2 cyclodextrins in 1 lipid in order to solubilize, not a 1-to-1 ratio. Just for fun, I also calculated micelle, and we're wondering which kind of shape the micelles will take, depending on how many lipids you use. And on the x-axis, you can see the number of lipids in the simulation, and on the y-axis is the average fitting error. And the average fitting error is generated from this upper graph. So if I have 50 lipids, it is, I can best fit a spherical shape to it. But when I increase the number of lipids, then I will not have the spherical shape anymore, but my fit will be more suitable if I take the blue one, which is an oblate shape as a fitting beam, in contrast to a prolate shape, which is more like a rod shape. So we can see that we have an oblate shape in when we get over 75 lipids is predicted, and we now have to verify with some experiments whether this is correct or not. But we hope this is the case. So in summary, this should just show that we can use DFT to understand the reactivity in order to see whether it is worth to try all the chemistry and the biology to test the system. So it's a combination of these three methods to get the optimum results and to understand what really happens at an atomistic level. And I have to thank, of course, all my collaborators also for the other projects, which I could not talk about today, and the funding agencies, and of course, you for your kind attention.
Well, thank you so much. Any comments, questions? Nothing? Oh.
So thank you for your talk. So you tested several versions of this charges, charge fitting methods. And so what is your opinion about all this? So what do you recommend? I mean, before that you showed, yes, yeah. So what do you heard?
It's a very nice and good question. So I only could test the molecular charges. I did the natural bond orbital charges as well, but I only have the standard one that I implemented in Gaussian because I don't have the license for the better ones. It looked a little bit better with the MBO results. I didn't calculate all of them, but my personal feeling is don't trust them in general. So it's a nice indication if it fits, but I wouldn't rely on it.
I mean, usually some people use this Pullman beam, this ESP. Yeah. So have you tried that or no? No.
Yeah, I have not tried that scheme, so I do not have experience how well it fits precisely. Usually I try, the first thing I do is I draw resonance structures and then I try to think whether they are possible or not. But this is just my own not so intelligent AI system, my personal one.
Another, I mean, I don't know if you have ever tried this. So it is known in quantum chemistry that this some functions like B3 functions, they have some problems when it comes to charge transfer, and many people uses this long range projection, so-called, to cope with this over polarization. Have you ever?
I did not use this one in this case. I mean, I could also try it with the MP2 setup now that I have the optimized structures because they are relatively small and not that expensive to calculate and see how the numbers change. But I think already the basic problem that you just divide the electrons half makes the probability that you end at the result that is close to reality a bit lower. So I mainly put this in order to remind people that you shouldn't trust these results so clearly. Thank you very much.
Any other comments? Nothing? So the time is running out. So thank you so much for our speakers. Then let's move on to the next speaker, who is next one. Yes, please. Professor Fielders cannot come here today, so then the next speaker is Ramsudat from UK, Malaysia, please.
Oh, so automatically share. Is there a pointer that? Ah, yeah, can you? Already? Thank you. Just check the slides, okay, right? Yeah. So hello everyone. I'm Sudat from University Kebangsaan, Malaysia, from Malaysia. I'm from the bioinformatics program. For me, it's actually a pleasure to listen to the talk of Dr. Peters. He's someone that I really want to learn from. Like, I mean, like become doing all DFT and D after so long and stuff like that. For me, I'm actually a structured bioinformatics. I don't do a lot of MDs, but when you publish a lot of paper, people starting asking you to do MD. So I started doing that. And then recently I met Dr. Watanabe. He said, should you try to do something neon as well? That's why you started having this topic, venturing through molecular dynamic transition from organic to inorganic. So I have half of my talk is on proteins, ligands, more inorganic, organic kind of thing. But after that, there's also something that I'll try to simulate neon and stuff like that. But it's not really working yet, just for spoilers. But it's ongoing process that I'm doing. So I'm showing pictures of my University Kebangsaan, Malaysia. It's here, the nature. There's nothing much we can show apart from the beautiful nature. It's just a joke there. We have all the nice food. Dr. Nagai was there as well. For my lab, basically, this is what I do. I focus on studying the molecular interactions of proteins and biological compounds. When I'm actually talking about that, we are actually looking at proteins and ligand, protein and DNA. So these are all the things that we can find within our bodies, and understanding them will be very important because you understand what's the functions of proteins. Understanding the function of the protein, you can start manipulating them. And sometimes this thing happen where it's something called mutations. So when we go out every single day, we'll be hit by UV from the sun ray. So it will cause mutations to happen. Or sometimes there's also something happening on our body that causes the mutations to happen as well. So all of these mutations is keep happening in our bodies and in our any organism around the world and stuff like that. So why do we want to study them? Because understanding about the mutations, you can start understanding what will be the impact on the proteins. So it may affect the protein stability. So meaning one of the mutation may be causing the protein to be destabilized. So if it's one happening in the core, that will happen to that. Sometimes mutations may impact the interactions with another proteins, the interface in the middle. So that may cause another protein not to work with another proteins. Maybe that will cause a cascade of effect not happening in your body. And on the right-hand side, towards the left, that one is more on ligand and stuff like that. So maybe a proteins or mutations is happening at locations where they're interacting with a ligand. Maybe it's a zinc domain, a zinc ion, or is a kind of like cofactor is not happening anymore. So it will stop the interactions from happening. So that will cause haywire in our body, and sometimes it could cause disease happening. So my research basically spread along three broad topics. So I'm very interested in viral host interactions. This started back in COVID-19. So at the time, I was just home. I didn't know what to do. And I started picking my model organism at that time. It was actually the SARS-CoV-2. But now we've moved on. We've added another one to the arsenal. We are looking at avian flu at the moment for the viral host. We also started working about on antimicrobial resistance. This is something that's happening where we don't really use the antibiotic very well. So for example, we eat our antimicrobiotics, but we don't finish them, or we just continue eating them. Our body basically got resistant to that. So we can't really kill this bacteria animal and stuff like that. So I've done some research on that. And the other part, because Malaysia and like Thailand, we produce a lot of props. So we need to go and do something on that and stuff like that. That's the three main topics that I've done. These are some of the sub thingy that I've done on that. So I'm just highlighting the two things in blue. So these are the two projects, a few projects that are more MD part. So when I started doing my viral work, there's a part we were asked by our reviewer to say, why don't you do MD simulation? And that's my first project. And I'll be talking about that in a bit.
And when in Malaysia, we have a lot of natural compound. It's the same in Thailand as well. There's a lot of natural compound, and people want to see what's the effect on that, on your body and stuff like that. So there's a lot of collaboration on that topic as well, that we use MD and docking to understand it. So we'll talk about that in our topic. And on the prop part, I'm not talking too much, but just to disclose, recently, most of my work is actually on trying to develop AI algorithm, where we want to figure out, is it possible for us to create predict some kind of mutation that will increase the yield of certain crops? And if I'm hinting it, then you probably can guess what this guy is doing. He's probably working on AI model that can predict something for the other two subtopic that he's working on as well. Just tell you, yeah. So that's it. So now I'm going more on the MD kind of work. So usually when we actually want to do biological kind of MD, we started with the first thing. You need to get the 3D structures of your proteins. To do the 3D structure of proteins, usually you may have closer. Okay. Usually you may just have the amino acid sequence of your proteins. So you need to predict the 3D structures of the proteins. Before that was very challenging, but recently that's because AlphaFold came in and you can model the 3D structures of your proteins very well with very high quality structural structures. There's also other software available, the iTaser. That's from the NUS. Professor Yang Zhang developed this group, and recently in the CAS competition, they actually came out to be better than AlphaFold and Rosetta 4. So if you want to use it, go for that. Apart from it, so when actually doing a modeling, sometimes you realize, okay, if a certain ligand that you're studying is not there, you need to start to do a process called molecular docking. Molecular docking is a process where you put the drugs on the proteins. So protein structures prediction is just a protein. Docking is the process that you put the ligand or the DNA or whatever that you want to study inside that. But just a disclaimer, this recent happens just like last year. AlphaFold came out with a new version. Rosetta 4 also come out with a new version where they can include the modeling of proteins, DNA, protein ligand as well. So there's some of you probably may not need to do molecular docking anymore, but this is just something for think. Yep. So once you have your proteins and the ligand, usually the next thing that you will do is the molecular dynamics simulation. And then you can try to move your molecules and create beautiful videos on your studies. So to do a biological system is usually kind of easy because all the fossil is already there. So we have Chiang fossil for proteins, the DNA, everything is there. We don't need to worry about picking the right one. And if you don't like Chiang, you can go for Gromos, Amber, or OPLS, whatever that is on the field, you can just get that. Software is also available. You can use Gromax, you can use Gaussian, you can use Amber, whatever that you want. All the software and all of the protocol is already there as well. So just a disclaimer, I'm a user mainly for the MD simulation. So for usually when you do a protein MD kind of simulations, for myself, I really usually want to focus on treating. I want to see what happened to my protein structures. What's the deviations you get from your proteins throughout the simulation? Do your proteins move a lot? Or sometimes we want to see what's the binding energy that happens. So if you're looking at protein and ligands, what's the difference in the binding energy that you can get? Is it getting stronger throughout the process or getting weaker throughout the process? And you can go into details as well, looking at the forces that actually form, like hydrogen bonds, salt bridges, or are the other like bonds that you actually want to see in the middle. And if you are actually focus on the solvent assembly, you can also work on that. So these are some of the things that I usually look when I do my protein kind of like simulation. Now I'm talking about my MD simulations. A note that I want to mention, before, when I did my PhD, I don't do any MD simulation. When I came back, I think it was like 2019, I attended my first lectures of MD, and it was actually from UM. I attended Prof. Vanajan's lecture in UM, and I was like, gosh, this is like a new field to me. And it's good that Prof. Vanajan is actually here for us with it and stuff like that. Yeah, so that's the story about my first MD simulation. So these was actually published in 2022. So I started learning about MD is just 2021.
So at the time, I was looking at my SARS-CoV-2, and then halfway of it, I need to do MD. Yeah. So most of the people are actually looking at the spike protein. So if you're actually looking at the spike protein, this is the part. So that's the spike thing that actually come out of the proteins. In that proteins, they have this spike-1 protein, S1 protein, and then there's like different domains inside that. So usually people just focus on the receptor binding domain, where it's the part that basically interact with the host proteins. However, apart from the major one, we also did some study on that, but we actually found there's a lot of mutation happening at another domain of these proteins, where it's actually something called N-terminal domain of these proteins. And then we started understanding there's a lot of mutation happening there. What's the function of this domain? So we started reading more about it. It seems like this domain is actually involved with a process called viral surfing. So what does viral surfing do? Is when you have your SARS-CoV-2 virus, this virus will basically bind to sialic acid that you can find on the surface of the membrane. So sialic acid, if you are not too sure what it is, just some kind of sugar. So the N-terminal domain will bind to this sialic acid. When they start to bind to this sialic acid, it will create some kind of a directional pull where they pull this the viruses towards the binding together with the ACE2 receptor, and then started facilitating the interactions at that time. So to take note, NTD is basically involving with the transmissibility. It's helping with a process called viral surfing. And then after that, if you actually want to study hard, because since I'm from a structural biofamily kind of way, we always need to understand the 3D structures of the proteins. We started thinking about where is the position where the sialic acid actually binds. So we figured out there's like 3 pockets of them. Some are experimental, some are like computationally predicted. And then after that, one thing that I did mention is we're seeing a lot of mutationing happening at this N-terminal domain. So our question is, where do this mutation actually lies? So we took a lot of N-terminal domain from the different type of subcoronavirus. And then after that, we find out where's the mutations. And then we figure out most of the mutations that happens on the right side of the proteins. That's all of the black part that's actually happening there. And then we coincide with the picture that we have mentioned to you. So the orange, the yellow, the blue, and the red is actually the sialic acid binding region. So it seems like there are a lot of changes actually happening on the right side, and it actually coincides with these sialic acid kind of pockets. And then it seems like there's a lot of mutations, and then I started thinking, what will be the effect on this kind of like different kind of variant? In order to do that, we started doing a molecular docking and also molecular dynamics simulation. So the first thing that we've done, for all the different SARS coronavirus variant, we created a model for all of them. And when you have all of the model for every single one of them, you can start docking the sialic acid to the different pocket. When you have docked every single one of them, you can now get some kind of initial binding energy of your certain structures to that. And then after that, you can get some kind of energy into that. I'm not going into too much details on the biology because I don't think you guys are interested into that. But basically, you will get some kind of binding energy for molecular docking kind of studies. And then after that, that is just telling you at a snapshot, this is what's happening to the binding energy. And we were challenged by our reviewer at that time. Why don't you do molecular dynamic simulation? You can simulate the systems for a longer period. And that was the first time me and my group started doing molecular dynamic simulations, where we do this. And the protocol we used was basically we use GROMAC, we use the charm force field, we add the ligand, we add also the water, add the sodium and calcium, you do steepest descent, you do it NVT, NPT, and you have the direction run, and then after that you got your data, and we see all of this. So we are just, throughout the process, you can see the top one is the original strain, and the bottom one is a more recent strain.
we can see that the red one, this is actually the sugar, and this is the proteins. Halfway of the protein throughout the simulations, the sugar already leave in the original kind of like thingy. But if you look at the Omicron variant, the more recent one variant, these sugar start throughout the process, that thingy. So it gave our reviewer at that time more confidence. Oh, this guy is saying Omicron is something that's more like bind stronger, is thingy like that. So yeah, we managed to publish our paper from that. So from that, we can also check the number of hydrogen bond you found throughout the process. We overall see that in the newer strain, there's more hydrogen bond forming from that. So that's a few years back's kind of work. And that was my first MD kind of simulation. And then after that, people started knowing, okay, this guy can do MD. And then they started talking to me. So I got a call from people from the chemistry department where they started to, they have their natural compound. And the one we're actually looking is called the curcumin, where it's actually from the kunyit, the ginger that you know. And they want to study, is it possible for it to be anti-malaria kind of compound? So these chemists basically, she created different versions of the curcumin, and then she chemically synthesized it. And then after that, she asked me to do the molecular docking for her. So you got some kind of initial binding energy. And then after that, we also help them to do the molecular dynamics simulation for her. And throughout the process, you can simulate the process. And it helped our friend to basically narrow down which of the derivatives that should work on. And the one that she figure out is actually have a more stable, so lower RMSD changes throughout the time, and there's forming more hydrogen bond throughout the process. And then after we narrow it down from a lot of compound to the best one, and we proceed to the experimental validation. And then we do find like this of the compound seems to be good in the experimental world. And we're not happy because we always want to improve. So my group now is actually collaborating with someone from Japan, where we actually want to improve our compound by adding sugar conjugate as well to make our compound even better. So after that, when we got the new compound, we'll do MD again and keep improving it. Yeah. I'm going to stop this because I've lost track of how much time I'm using. After that, we also do peptide docking as well. So I'll skip that. Okay, then after that, that's the second part of my story. And it was actually just last year, Dr. Watanabe Chase came to UKM and stuff like that, and started talking about Meon. I was like, gosh, I've never thought of Meon in my life. And I was like, cool. But the only thing that I get from him is Meon can actually help us to track the local magnetic environment of a certain thing. So that's so cool because previously we can't really track the magnetic environment of DNA or RNA that well. So it seems like it's a good probe we can actually use for that. So I started thinking, is it possible, can we use Meon to further understand our organic or inorganic kind of molecules and applying to our proteins, DNA, and also inorganic kind of molecules? And then I went online and studied, okay, what kind of proteins should we start looking? So we can look at cytochrome C or DNA to studying the electron diffusion throughout the process. And then I came across Dr. Fadila's paper. She has been working on DNA for some time. So she started doing Meon spin spectrophotometry to understand the DNA. Like, gosh, seems interesting. And I'm from a computational kind of background. And I started thinking, is it possible for us to simulate the interactions using computer? And after that, I started building this table. In order to simulate Meon, probably there's few methods. The most powerful one, in fact, it should be the DFT that Meon, that Dr. Fadliba has been working on. So it will give you the most accurate result on the electronic structures, bonding, and thanks to Dr. Peter's kind of lectures, he talk about homolumo and every single thing. So you can get all of those calculations and everything so well. But the bad thing about DFT, it just tells you at that specific milliseconds or nanosecond or whatever seconds at that point as well. And we cannot simulate process for a longer period, like a 1 nanosecond and stuff like that. So for that, we need to do a process called molecular dynamic simulation. And for me, when I started looking at it, and it seems like you can use molecular dynamic and start collecting different things. So you can also check their mean square displacement, meaning how throughout the simulation, how far the muon can move. How's the hopping rate throughout the simulations, the residence time throughout the process. However, currently, there's no muon force field at the moment. Luckily, we heard the talk by Dr. Nagai and Dr. Shiga mentioned you can use molecular force field, molecular dynamic to create the force field for that. So that's something that we should work on. And there's also some people that started thinking, if we don't have a force field, can we start doing something called QMMM, where it's something in the middle. So QMMM meaning it's the QM is the part that you will do the muon part that you will do the DFT. The MM part is the one that you will do on the protein. So protein, you have a force field, you can basically just do the normal MD for that. But the QM, you do the L1. You can still get the MSD, hop rate, and every single thing. But now it's still kind of rare. No one really has started doing the muon thing on this yet. So my ultimate wish, I do wish that we can use QMM or MD to simulate the myonic effect in the future, but I know it's not possible now. Yep. So while after that, I went to Japan for an attachment for 2 weeks. And then after that, I started doing something. It's just my baby steps. And I told you already, it doesn't work. Yeah. So I just started thinking about it. So we can't do DNA, we can't do proteins. Why don't we start to do something simple? Something called copper metal, stuff like that. Yeah. So I went to the material studios. I think it's one of the material projects kind of website, and I got my copper metals, and then that's the value that you get. And then after that, I prepare my cobalt metal, and then after that, I decided you want a software called LAAMPPS, the one that usually people started to use. And then you get the structures, you convert them into a supercell, and in my cell have like lots of cobalt inside there. 125 of them. And then after that, this is software, you need to install them and make sure it works. And for the force field for the cobalt metal, it's just because what I've done is just I'm not using my PhD student or master student doing it. It's just myself spending just for 1 week to work on the 1 hour every week just to do my project and stuff like that. So I started learning about force field on cobalt metals. So far, I've just managed to found 2 simple force field that's on the cobalt metals that's actually available. One is called EAM and also MEAM that's actually available. And out of these 2, the MEAM seems to be better, but it's not perfect yet. There's other type of force field that's available. For example, I think Dr. Shiga just mentioned about one. Is it tip building? Is it? Yeah, one of force field that's even better that's available, but I haven't used that yet. But so far, I'm just exploring both of these force field, and I've managed to download from the website for the cobalt metal. And then after that, for the muon force field, because there's no muon force field at the moment, I've just started just using very simple one, just using the Leonard Jones force field, the simplest force field that available, where basically it describes the non-bonded interactions between the neutral atoms and the molecules. And it doesn't give all of this, the properties of muon, but just for the start. So they don't have muon charge, they don't have muon spin interactions, no quantum tunneling and every single thing. That's the command inside LAMMPS. And then after that, for the MD, you do energy minimization, you do MPT, NVT, and you do the simulations for 0.2 nanoseconds. And this is what I get. On the left, this is the EAM. On the right, this is the EAM. This one, I decided to show both of them so that it's easier for you to track them. So for the EAM, you can see that my muon basically just stuck there the whole time. They don't really move, and it's just stay at that location. For the DEAM one, there's more movement into it, but I don't think that's perfect because it should move more throughout the process and stuff like that. But this is just my baby steps into it. And if we just look at the mean square displacement, this is for the EAM. It's not really showing a lot of movement, but my DEAM shows more movement going up to like 8 angstrom. However, when we actually do this kind of simulations, we always need to go back and read the literature. And then Dr. Watanabe suggests me to read this paper. And according to them, if you have for muon, the hop rate basically should, when they actually like more than 100 kilodelvin, the hop rate should be very, very fast, and it should be keep increasing throughout the process. And you actually go, follow my talk. What I'm doing is actually started from 300 to 600. It's actually way higher from this kind of paper and stuff like that. So from 300 to 600, but for me, I'm seeing my initial kind of run, there's some kind of plateau actually happening there. And then if you actually just look at the diffusion coefficient, it's not really that high. It should be even higher when you actually do the actual calculations with a higher kind of temperatures. So it's too low at the moment. So this is showing the simulation is not really perfect. I would always need to go back and start defining a better force field for my muon, for my cobalt metal, so that I can do a better simulation. And maybe we can also derive the force field for the muon, for the DFT with the help of ML. And then I also do something when I try to do the DFT on the cobalt and the muon, but so far it's not really working yet. My DFT just stopped at the SCF kind of part. So I'm still trying to do it. I should have talked to Dr. Fadila. Yeah. And yeah, so in my talk, I do mention about QMMM. My QMMM is also in the process of doing it. I didn't manage to get it to be correct at the moment as well. Yeah, that's just the part. Thank you so much. I want to thank Nexus for providing the grant for me to come here, and also went to like Japan for the transfer program. I want to thank the Ministry of Education for my other work, and also recently from the UK Medical Research Council for my newest grant on avian flu. Thank you so much.
Thank you. Any question or comments? Nothing? Okay.
Thank you so much for your presentations. I just have just a little question about the force field setup for the muon particles inside the copper that you simulated. So how did you assign the Lennard-Jones potential terms inside the muons?
To assign that one, I just tell you the magic answer. I asked ChatGPT to help me to assign. Yeah, I should have studied more on that, but basically, yeah, if you follow the thing, what I use is basically, yeah, those kind of cutoffs like that. Yeah, it's not perfect. But I just want to start getting the simulation going so that I can start doing something that's a bit different, because in protein kind of world, it's easy. The right force field is already there and stuff like that. But now I need to start thinking about force field, installing them and getting them. And it was so hard. Yeah, that's why I adore every one of you can do inorganic system. Yeah, thank you so much.
Well, I mean, yeah, I mean this mean the modified EAM is a standard way for this for this system, metallic system. So I have nothing to say about it. Yeah, I mean, it's just but if you can do it with machine learning potential, maybe it's better. But yeah, I mean, I don't have complaints about this.
Any other question or comments? Just I have comment regarding the muon diffusion. As long as experience, the especially for inorganic systems. Organic system, it's not so easy to see the diffusion. But generally, the and many materials has the like a diffusion temperature to be around 100 Kelvin, 150 Kelvin. We are not so sure why. Even for high TC, it's a very strong correlator system attached to the mu and a very strong potential, but still about 150 Kelvin, mu start to diffuse. But generally, my understanding is generally in organic systems, the muon start to move around about 100, 150 Kelvin.
Yeah.
We don't know why. Okay. So then thank you so much for speakers. So now is a time for lunch. So lunch somewhere.
So thank you to all the speakers. So the lunch will serve as the same room we have break, and we will back again at 1:30. So please enjoy.
Okay, so welcome back to the afternoon session. So my name is Sakon Rimjam. I will be the chair for this section. So I think it's time to start the first talk of this afternoon. So the talk is related to MD simulation for protein. So the talk title is Coactive Gases Antarctica. If maybe better you say it by yourself, but the talk will be given by Dr. Doris Quay. So let's start your talk, please.
Okay. Good afternoon, everyone. Thank you for the invitation, Dr. Watanabe, for me to join this seminar. So my name is Doris Quay. I'm from Malaysia, University Kebangsaan Malaysia, UKM, Department of Applied Physics, Faculty of Science and Technology. And disclaimer, I'm actually not a computational biologist. I'm an experimental person. But a few years ago, I tried to learn and teach computational molecular biology. And also try to do some MD work as well. Okay, so today I would like to share some of the work that we have been doing on characterizing structure and function of arginase from Glaciozyma antarctica. So it's actually a co-active enzyme, co-active arginase. And through reviewing or determining the crystal structure, we found that this arginase contains many structural flexible region, okay, around the active site and also the protein surface. So we use MD simulation to study the protein flexibility. Okay, so I give a bit of introduction. What is Glaciozyma antarctica? So it's a psychrophilic yeast that live in Antarctic. So this yeast was isolated from the Antarctic sea ice, which is a very cold, extremely freezing cold temperature region. Okay, so how does this yeast can survive or thrive or live in this very cold, freezingly cold environment, right? So it's actually adopted many mechanisms to prevent the cells become frozen, right? So that's why this yeast produce many unique enzymes. For example, anti-freeze proteins, ice-binding proteins to bind to the water molecule and prevent the water molecule to become frozen, become ice. And it's also produced some desaturases enzymes to prevent the membrane, cell membrane, to become frozen. Okay, so the cell membrane is still very fluidity. And also some heat shock proteins to counter the stress, and also co-active enzymes. So these co-active enzymes is very special. So it different from us, like mesophilic organism or thermophilic organism. So co-active enzyme is known to have structural flexibility. Okay, their structure are flexibles. And this flexibility will reduce the intermolecular interactions so that they are not rigid and cannot do the catalysis, right? Okay, so the arginase is one of the co-active enzymes from GA. And it catalyzes the hydrolysis of L-arginine to, share screen. Okay. So this arginase catalyzes the hydrolysis of L-arginine to L-ornithine and urea. It's a very important enzyme that present in many organisms, including human and also other animals and microbes. So in human, it's very important to remove toxic ammonia from our body, okay, in the urea cycle. And in microbes, it helps the microbes to colonize and also pathogenicity. So that's why a lot of the research has been doing to design inhibitors to inhibit this arginase function that are associated with disease and pathogenicity. So to study the biochemical properties of this arginase, we need to produce the recombinant proteins. Okay, so to produce recombinant proteins, we have to synthesize the full-length gene, clone the gene into E. coli expression system, express the protein and purify the protein into a very pure protein like this, shown here with one single band on the SAS page. So after we got the purified protein, then we can start to do biochemical assays. Okay, so and then the result shows that this arginase is catalyzed the best activity at 20 degrees Celsius. Okay, so 20 degrees Celsius is very cold, like colder than the normal temperature, ambient temperature. Okay, so at 10 degrees Celsius even, it still remain 50% of the activity. So it's a coactive enzymes. And optimum pH is at pH 9. Arginase is a metalloenzyme, so it needs metal ion to act as a cofactor to help with the catalysis. So it requires the best metal ion, which is the manganese ion, as a cofactor. But it also can accept other metal ions, actually, so including cobalt, nickel, and potassium. And but it's also sensitive to some of the chemicals like SDS and EDTA. It's connecting. Sorry about that. Okay. No. All right. And this arginase has a very specific substrate specificity. Okay, it only catalyzes hydrolysis reaction on L-arginine, but not D-arginine and L-carnitine. Okay, and then we compare with other arginases from the other mesophilic and thermophilic, and indeed you see, so ours is the lowest, has the lowest temperature, 20 degrees Celsius, but others are catalyzing at 30 degrees Celsius or 100 degrees Celsius. So co-arginase can be applied in many industry like beverage, food and beverage industry or detergent industry. So to study the three-dimensional structure, we need to do X-ray crystallography. So the purified protein will grow into these protein crystals. Okay, and then we shoot this crystal with X-ray radiation. And then we collect the diffraction data, all right, images. And then we use computer to process the diffraction data and do molecular replacement to solve the crystal structure and do many rounds of refinement and model building to finally get the real crystal structure. And then we deposit into the PDB. So this structure was solved at 2.35 angstrom. And this is the crystal structure. It looks like this. So it has it's a alpha, beta, alpha sandwich fold. You see this here has 8 parallel beta strands in the middle and surrounded by 8 alpha helices, 9 alpha helices at the side, connecting with actually many loops here. However, when we try to build the model according to the electron density map, we saw actually there are 5 regions of missing electron density region, right? And why is that? So usually missing electron density region means that these regions have a secondary structure or loop region is very flexible or disordered. So when we compare this structure with other homologs, these regions are inferred as flexible loops. Okay, so here I show flexible 3 at the active site, around the active site. So this is the active site pockets which we superpose with ligand. So this is the active site pockets, and here is the flexible, putative flexible loops that have missing electron density, loop 1, loop 4, and loop 5 around the active site, and 2 others are loop 2 and 3 at the protein surface. And then we look at why it's flexible. We look at the amino acid composition around this flexible region, and we found out that this missing electron density region mostly compose or contains many small or uncharged amino acids, like alanine, serine, valine, and threonine. Whereas the thermophilic ones at the equivalent position, they contains more charged residues. Okay, the arginine, glutamic acid, histidine, and so on. So the small, like a small and uncharged amino acid will mix less interaction, intermolecular interactions. So that makes them flexible. And then we look at the active site pockets, and you can see that GA arginase has a wider and shallower negatively charged pockets here compared to the mesophilic and thermophilic arginases, which you can see actually it is smaller pockets, smaller entrance, and deeper pockets there to bind with the substrate or ligands. So we hypothesize that because of the presence of flexible loops around the active site, so it makes the active site become wider and more open for the substrate to get into the pocket for the catalysis in the cold environment. So as a summary, we have characterized the first co-active arginase biochemically and structurally, and it works best at 20 degrees Celsius, very low temperature, and also have many flexible loops around the active site and the protein surface. And then next, we are interested to use MD simulation to actually study this flexible region, how these flexible loops actually move, how fast does it compare to other homologs, right? So we analyzed these three analyses. The first one is we set up between 20 degrees Celsius versus 37 degrees Celsius. The second one is the apo structure versus the ligand bound structure. And the third one is L-arginine versus a thermophilic arginase. So before running MD, we need to set up the protein system. So we use ChamGui. So first of all, we have to get the PDB file for the protein and prepare the protein. That means to remove all the ions, water molecules, or ligand that are not necessary, right? We have to remove them and then add nitrogens to the atoms and also the charge to the system. And then we set the pH to 9 because it's optimal for GA arginase reaction. We add NaCl, we then select amber phosphyl because amber phosphyl is good for protein and protein ligand MD simulation. We use GROMAX, and then we also set the temperature to the optimal one, which is 293 K or 20 degrees Celsius, which is the optimal temperature for GA arginase. And then we set for MD to run for 100 nanoseconds. So it will generate these inputs. Okay, so once it's finished, then we will get a script. And then we need to modify a bit on the script before running GROMAX. So I run my GROMAX on my PC, which has one GPU, and it usually takes around 36 to 48 hours for a protein that contains 300 amino acids. Yeah. And then when the GROMAX has finished, then we use XMGrace and VMD tool to analyze the trajectory movie and also the plots. So, from this movie, you can see that, okay, so here is the loop 4145, which is around the active site here. This is the pocket around here. So you can see the loops is actually very flexible, moving a lot. And this one compared to this region. So these are more flexible region here, right? So this is 20 degrees Celsius versus 37 degrees Celsius. And you see they are moving, but they are not covering the active site actually. So they leave the active site white and open so that to allow the substrate from getting into the pockets for catalysis. But we cannot quantify, right? You see they move very fast, but you cannot compare whether this is faster or this is faster, right? So we need to look at the plots. So when we compare the RMSD plots, it shows that yes, I mean, GA arginase at 20 degrees Celsius is much more flexible because you see the fluctuations here is much more higher than compared to this one at 37 degrees Celsius. And also RMSF also shows these fluctuation peaks are higher than compared to this one. Okay, so sorry about that. So again, this has a higher fluctuation compared to the 37 degrees Celsius one. For the second analysis, again, you see this, but it's very hard to compare between these two systems, which is the cyclophilic arginase versus the thermophilic arginase. And we look at the RMSE plot. Yes, you see these are flexibles. Again, these are very fluctuating compared to this one, quite flat and stable. And then the peaks, but the peaks around the loops region are also higher than this one. So again, the cyclophilic flexibility is higher than the thermophilic arginase. And the third analysis, okay, so for the third one, so which is the APO means only the protein doesn't have the ligand, so and versus the ligand bound, arginine bound complex. Okay, so we hypothesize that the APO one will be much more flexible. The ligand bound one will be more stable. And indeed, you see this fluctuation again here, and this is very stable, right? After binding with the ligand in the pockets. And we compare RMSF, yes, the peaks 135 loops region have higher fluctuation rates compared to this one are all very low amplitudes value. And we also look at the minimum distance between the protein and ligand, and you see a very short distance between the protein and ligand interaction. So that indicates that the very strong interactions and the ligand keep binding into the protein pockets throughout the simulations without getting off. And the hydrogen bond analysis shows that there are around 5 to 6 hydrogen bond forms between the protein and ligand binding. And also, we also look at binding free energy results between L-arginine and also L-ornithine. And indeed, you see very high negative energy value, which shows that it's a favorable binding energy. So it binds very strongly compared to this one. Of course, this one, because L-ornithine is actually the product of the hydrolysis. So of course, when the product is formed, then it will be released. It will not bind in the pockets. And it's also this plot shows which, we tell you which amino acids in the active site catalytic pockets are contributing favorably into the binding to the protein, right? To the ligand, so which is this one, aspartate 111, aspartate 135, 139, 2A. And some of these enzyme amino acids are indeed the identified putative catalytic residue. Yeah. So as a conclusion, I will say that MD simulation indeed support and verify our experimental observation in terms of the protein flexibility, and also give us many detailed information on, especially on the protein ligand energy binding and amino acids that bind favorably. So that's all for my talks. Thank you so much for your attention.
So thank you very much for Dr. Doris. So any questions from the floor?
Your talk is really interesting. I'm from industrial chemistry. What about your concept or your perspective of your work will be applied maybe in the future or in the recent knowledge? Yes.
Yeah, so far I haven't from the literature, it's very hard to quantify the protein flexibility. Very hard to quantify. So people are just reporting maybe less hydrogen bonds formed between this and this, less those arginine residues, those proline residues. It's very hard to quantify like in percentage, maybe how much fluctuation, how much flexibility for this cyclophilic enzyme compared to mesophilic and thermophilic. So yeah, with this MD simulation, it gives you fluctuation rates, right? The value. So you can actually tell the number actually how much it's flexible, the flexibility rate greater than the others. Yeah, that's what I think.
I also have additional question to that. So how large of your system, simulation system, in order to demonstrate the comparison with the experiment?
How much? Sorry?
Yeah, how large of your system in
Like,
simulation?
320 amino acids, about 50,000 atoms, I think. Yeah.
Okay, thank you. The microphone.
Thank you very much for the nice talk. When you made the simulation with the ligand bound, did you see a conformational change of the flexible loops? Because you say they are less flexible, but why are they less flexible? Do they have interaction with the ligand? Is it the ligand pulling them in and forming a pocket once it is bound, or do they stay in the same area as before?
So once the ligand bound, the conformation of the pocket, yeah, it will have the induced fit mechanism. Of course, the pocket will become fitting much more than the apo form. And the amino acids that contribute to the binding are shown in the decomposition analysis. So we know which amino acids are actually bind very strongly to the ligand.
Yes, but the position of the loop, because initially you showed the loop is relatively far away from the pocket, so you say it's open, but does it move in?
Yeah, actually, it's a bit, well, yeah, I think it's coming closer to the inside of the pocket, yeah, compared to the apo.
Yeah, so it gets more closer to
To
the high
the-
temperature protein shape.
Yeah, yeah.
Thank you very much.
Okay, so any more questions? So if not, then let's thank the speaker.
Thank you.
Then we move to the second talk. So the second talk is Dr. Wan Saharim, right? Okay, so the Dr. Wan Saharim will give a talk related to the DFT simulation with muon in the topic of unveiling the structural and properties of polymer and biopolymer using the DFT and muon techniques. So Dr. Saharim, ready? So please start. Yes.
Okay, Assalamualaikum warahmatullahi wabarakatuh, and a very good afternoon to everybody here. So thank you for being here today, and thank you for inviting me to give some talk about my project, my group project. So the title of my presentation today is unveiling the structure and properties of polymer or biopolymer using DFT and muon techniques. So my name is Wanur Fadlim Dizarim. So I'm from Department of Chemical Sciences, Faculty of Science and Technology, University Kebangsaan Malaysia. Previously, I worked in University Science Malaysia. So I just moved to University Kebangsaan Malaysia in 2023, December 2023. So this, I think Dr. Suda already showed some photos of our university. So this is some photo of the University Kebangsaan Malaysia. So it is actually located in Selangor, as you can see here. Here is the Kuala Lumpur. I think KLIA is around here, and this is where is University Kebangsaan Malaysia is located, which is in Bangi. Okay, this is our faculty building. Okay, under Faculty of Science and Technology, there is a few departments. This is all the six of the departments. So I belong to Department of Chemical Sciences, and we also have Center of Excellence. So for me, I'm under Polymer Research Center, which is we call PORCH. Okay, so now we are moving on to my research. So basically, most of the time I use density functional theory. I think most of you here knows about DFT. This is just some basic information about DFT, DFT quantum mechanical method. We use it to study atoms, molecule, solid. So it's involved the full many body Schrodinger equation. DFT simplifies the problem by using electron density as the fundamental variable. So in other words, so DFT transform a complex many electron problem into a more manageable and by focusing on the electron density and a wave function. So these are some of the examples of calculation based on DFT. First is the predictive calculation of optical properties. If you would like to know more, maybe you can go through the paper. So from this paper, they developed a first principle theory of for non-assisted optical absorption in semiconductor and insulator. And then we use also DFT is also used in materials characterization via vibrational spectroscopy. For this study, they perform a joint computational and experimental study of the infrared absorption spectrum of hybrid halide perovskite. And we also use DFT on computational material discovery. For example, is this on this paper, they use computational design and the experimental synthesis of a new family of PB-free inorganic halide. Okay, why is DFT so popular? Is this is some of the reason why I think most of researchers would like to use DFT in their study. So the first one is transferability. We can use same code method for very different materials, and then simplicity, reliability, software sharing, and robust platform. Yeah, maybe you can read more and see whether it's true or not. So for my study, this is some of the computational study that I have been done throughout these few years when I start doing research. The first one is a gold nanocluster, and then biopolymer and polymer-based. Polymer-based solar cell. So firstly, I will talk about the biopolymer, which is for my case is DNA. So DNA, this is the structure of DNA. It is in double helix structure, and as you can see, the outer layer is the sugar phosphate backbone, and we have the nitrogenous bases in the middle of the DNA. So there is 4 nitrogenous bases in DNA, which is adenine, thymine, guanine, cytosine, and there is a complementary base pairing. Adenine will pair out with thymine, guanine will pair out with cytosine. So DNA can be in few different forms. So this is some of the example. Actually, there is more than this, but this is some of the example for the DNA conformation. Some update on DNA, there is DNA origami. So DNA origami used in biomedical application such as biosensing, targeted drug delivery, and cancer immunotherapy. And then some chemists also use DNA to build world tiniest antenna. So if you would like to know more, maybe you can read this article. It's like a two-way radio that can both receive and transmit radio wave. And they focus on the fluorescent color to see to sense the movement of the protein. And DNA is also used as nanowire and nano device. This is this paper is in 2016. As you can see, although it's old paper, people already go into see whether DNA can be used as nanowire or nano device. This is some other articles that talk about DNA, electron transport in DNA, and how electron is transferred in DNA. And then for my interest, how to study the electron behavior in few DNA forms. So that's why we need a microscopic probe. So can we actually differentiate the electron behavior in few different DNA forms? So it is because as we know, the electron behave differently in different potential. So for my project, we combine the MSR and computational study, and to get to see the details on the magnetic or electronic structure, dimensionality of electron transport, muonium hyperfine coupling constant, and electron diffusion rate. So this is some of the paper that already published on the electron transfer in DNA, and they look the properties is by using muon. And this is the second paper, electron transfer in protein as probed by muon spin relaxation. So to understand the electron transport motion, so we need the Rishke model. So this is the equation that involve. And if we look closer, we require the value of muon hyperfine frequency value to get the muon spin realization function details. So that's why I'm focusing on finding the muonium hyperfine coupling constant in DNA, one of the reasons. So in a complex system, it is actually difficult to determine the muon site and muon hyperfine coupling constant. So as such as polymer-based solar cell and biopolymer. So we actually need a reliable technique to understand the muon site and muon hyperfine interaction. So this information is very much needed to understand the electron transport behavior in material of interest. So one of the paper that I always refer to is this paper. So they use a avoided level crossing muon spectroscopy to find the muonium hyperfine coupling constant by experiment, but they find it is difficult because they use real DNA. They don't know the real structure, the real sequence of the DNA. So this is the result that they get, and they cannot really discuss in detail what is the spectrum means. So why DFT is important to study muon site in DNA? Because the location of muonium trapping site position is in DNA determine the muon hyperfine interaction. So muon hyperfine interaction is highly sensitive to the electronic structure around the muon stopping site. So DFT can actually provide the accurate value of muon hyperfine interaction, and subsequently the resonant field for ALC spectrum can actually be predicted. So this will help you to plan the ALC experiment, so you get the accurate muonium hyperfine coupling constant value. And then because based on our group work, so the DFT actually able to predict the muonium hyperfine coupling constant value in the correct range. So then the DFT can actually provide the accurate electronic properties. So it will provide the homolumo gap, correct value of homolumo gap, and so on. And Further than that, we also try to look into the non-covalent interaction. So what we found out that the FT provide the accurate description of non-covalent interaction in the around the muon stopping area. Okay, as I told you, there is 4 nitrogenous bases. So what I do is firstly I try to see the possible muon triplex site in one single basis. For guanine there is 8, for cytosine is 6, adenine 8, and thymine 6. So I try all nitrogenous bases and I put muon at all possible muon triplex site. So yes, I use the FT. So we need to select the functional basis set and the correct geometry. So this is the list of basis set that I already tried. I think it's 18 or 16. I can't. 1, 2, 3. Okay, so it's 18 basis set. So I tried all these basis set for each muon triplex sites. But for today, I will show only part of the data. So for example, for cytosine base, this is the where I put muon there. As you can see, 1, 2, 3, 4, 5, 6. There is 6 position. So this is from the experimental result from previous study, which is I think Ian Mackenzie paper. So actually, what we get from the computational study is similar to the experimental value. So we believe that our method in finding the muon hyperfine coupling constant for small molecule is quite accurate. So we find out for cytosine, for example, we find out that when we put muon at this position, it has lowest total energy, and the value is also around 420 something. Okay, besides that, as I told you, I try with few different basis set because I want to see which basis set actually provide the correct value of muonium hyperfine coupling constant. So what I found, so from here, what I can conclude that the lowest basis set, the smallest basis set have the value which is nearer to the experimental value. This is the experimental value from previous study. So this is the value that I get from my calculation. So 61G is the closest one. But in terms of energy, of course, the most expensive basis set give you the lowest total energy value. So this is quite important for me because when we try to move to bigger system, I mean to double strand DNA with more than 1 or 2 bases, maybe up to 12 or up to 100. So I cannot use most expensive basis set. So it will give me some trouble. Yeah, the resource is not enough for me to use the most expensive basis set for my calculation. So that's why I want to look, is it okay for me to use the lower basis set to study the bigger system? So it turns out for the hyperfine coupling constant value, you can rely on the smallest basis set rather than the bigger basis set. This is some of the data. I compare with this one is the lowest basis set, and this is the most expensive basis set here. So as you can see, it's the muonium site stability is still the same, but you can see there is a difference in hyperfine coupling constant value. So this is the 631G. This is the 6311 plus GDP, as you can see here. But when you compare with the experimental value, you can see that 61G provide the nearest value compared to the most expensive basis set. So this is one of the, how to say, proof that although we are using small basis set to find the hyperfine coupling constant value, it is actually reliable and we can actually use the basis set. So this is for thymine. Same, I compare between the two. Okay, after study the nitrogenous bases, we move on to the single strand DNA. So these are some of the structure that we have tried, which is 12-mer single-strand DNA, guanine, adenine, cytosine, and thymine here. So it's actually took a long time to optimize the structure. For this one, I use Bridge 631G. That's why I need a reason why I can use 631G only. So because although this is only 12 single-strand DNA, it took more than 35 days. This one is without error. If you encounter some error and then it is, you need to repeat all the calculations. So for this system, the number of atoms is 411 atoms. So 2050 electrons, and the basis function is 2725. So I try to put muon at all possible muon trapping site. As I said before, if one nitrogen is base of guanine, there is 8. So now we have 12 guanine in one system. So the total is 96. For 12-mer cytosine 72, and then 96 and 72. So I try to put muon at all position, and I tabulate the data into this kind of figure. So from what we can see here, this one is for guanine. Still, the possible muon trapping site for guanine is C8. This is similar to the previous experimental study, but not for 12-mer single-strand guanine, but it's only for the one nitrogenous bases, because we don't actually have the data for 12-mer single-strand DNA yet. Then this one is for cytosine. We got the similar result with the previous experimental study. Same goes to the other two 12-mer single-strand DNA oligomer. So we could see the stable muon trapping site for our study is quite similar to the previous study, but the previous study is on the one nitrogenous basis, but for this case is you have 12 nitrogenous bases in one molecule. And then we move on to double-strand DNA. Okay, we already done for the guanine cytosine double-strand DNA, but for today I will only show you for the adenine thymine double-strand DNA. This data is not published yet. It's on its way. So I try starting from 1 base pair and then move on to 2 base pair, 3 base pair, and 4 base pair. Currently, we are only able to do up to 4, because when we try to move to 5 or 12, I cannot converge the calculation. So we need to find another ways to do that. Okay, but for this data, we notice something different. It's not the same as the single-strand DNA. So for this side is the 3 base pair. This one is 4 base pairs. So the difference is this. This one is 3 base pair and this one is 4 base pair. You have an additional base pair here. So this is the comparison between the two. You can see below here, for the 3 base pair double-strand AT molecule, it is consistent. So C8 and the yellow one is C6. Is the most stable muon trapping site. But when we move to 4 base pair double-strand AT, you could see that there is some other stable muon trapping site here. Not only this yellow and red dot only. So we want to see why is it like this. So that's why we do non-covalent interaction method. So from this NCI method, we can identify and characterize weak non-covalent interactions such as VDW forces, hydrogen bond, and repulsive interaction around the muon trapping site, because as I mentioned before, muon is sensitive to the local electronic structure. So this NCI method relies on the reduced density gradient RGG analysis, which allow for the detection of non-covalent region in the electron density. So actually you can plot it and you can see the different color to differentiate hydrogen bond, VDW interaction, and steric effect. So this one is for, okay, this one is for 4 base pair and 3 Originally, entry is not the most stable muon trapping site, but when we do it for the 4-base pair system, entry is the most stable muon trapping site. So we want to see why is it like that. So this one is before we put muon in, and then this one is after we put muon at the entry position. So as you can see, the sugar phosphate backbone and the nitrogenous bases become closer when there is a muon at that position. So this is the graph of the RGG versus this is, but we can actually plot this into the surface. When you plot the isosurface, you can see there is a hydrogen bond between the oxygen and muonium when muonium is trapped at N3. And this one is the sugar phosphate backbone area, but this is for 4-base pair. And then we try to compare to the 3-base pair. Why entry A site in 3-base pair is not the lowest muon trapping site? Because we could see that there is no hydrogen bonding between muon and anything closer to it, like oxygen. So that's one of the difference why we could say that one of the different why entry in 4-base pair is the most stable muon trapping site, but not for entry in 3-base pair system. So yeah, the calculation took a long of time. So one of the way how to increase the calculation speed, I also try to use the FTB plus. So this is the data for the 6-guanine, what I have currently. So this the starting point of the initial geometry is the same for both Gaussian 16 and the FTB plus. So I try to see what is the difference after I've optimized by using two different things. So by using Gaussian 16, this is the result, and this one is for the FTB plus. So if we compare the energy, Gaussian 16 produce structure that have total energy 5 EV lower compared to the FTB plus. So for this one, it took 5 days, but when you use the FTB plus, it took only 3 hours, less than 3 hours. But the HOMO-LUMO gap value is still similar. Then I try to compare the muonium hyperfine coupling constant value and see is there any different. Yeah, there is some difference between 631G, the FTB and using the FTB plus. As you can see here, both of the method produce give the result that B6 is the lowest muonium trapping site, but the value is quite different from one another. This is quite important because muonium hyperfine coupling constant value is sensitive to the local electronic structure. That's why I really want to see which method actually provides the correct value of HFCC value. So beside hyperfine coupling constant, I also look into the HOMO-LUMO gap. This one is the HOMO-LUMO gap for the single guanine, but the difference between these two is when this is a CH3 attached to here, but this one is sugar phosphate backbone. So I want to see the difference. And then we also see the difference between the 12-mer single strand DNA. From here, we could conclude that guanine has the lowest HOMO-LUMO gap. And then we move on to the double strand DNA. And this is the data for double strand DNA. So what we can conclude from here, the highest occupied molecular orbital still at guanine, which is guanine is the most conductive part in the molecule. And then this is the comparison of the HOMO-LUMO energy gap. As you can see, when we move on from single to 12-mer, and then we move to double-strand DNA, and we modify by adding some methylated group to the molecule, it gives you different HOMO-LUMO energy gap value. So DNA is actually a versatile biopolymer, so it can be in few different form and it can be synthetically prepared. So homolomo gap is also important parameter in the selection of the polymer or biopolymer material for solar cell. The discrete energy level of DNA molecule also affect the optical properties. As you can see that the homolomo gap is easily be changed when you change the DNA sequence. So DNA molecule might have similarity with polymer and solar cell because there is a many carbon ring, many similar local electronic environment. So the next thing is I try to perform calculation on this polymer P3HD. So this is quite new. I asked my student to do it. So we start from one monomer and then we increase. Now we increase up to 8 monomer. So the same thing we do with DNA. We try to look for the muon trapping site and homolomer. This is some of the homolomer data. And this is the latest data that my student have, but I didn't put the detail here yet because she is now writing her thesis. I'm waiting for her to be free and then give me the results. So, so how to move to the next step? So I'm not an expert in machine learning, so maybe we could combine machine learning and molecular dynamic to predict the hyperfine interaction. And then we can use machine learning and molecular dynamic model to suggest polymer or biopolymer sequence or structure that produce desired properties that we want, maybe by changing the optical properties and which one have the lowest homolomer gap, which one can give you the most stable sequence or structure. So predict muon hyperfine coupling constant and homolomer gap of polymer or biopolymer using, this is one of the suggestion, but I don't know whether this is a good suggestion or not. Maybe I will try to like make revision more on this. So maybe you can use graph neural network and DFT. So from graph neural network can predict the hyperfine coupling constant value and homolomer gap in the design or engineered polymer or biopolymer system. So we have the polymer biopolymer and then we do the FT calculation and we get the graph and then we use GNN and then we get the properties that we wanted. So maybe this is, I don't know whether this suggestion is correct or not. How can we use GNN in the this research? So we can use the FT to calculate the FT data set of the polymer and biopolymer and then convert molecules to graph and then train the data and then predict the properties of new polymer or new sequence. And some of maybe the advantage of this approach is rapid property prediction, scalable to long polymer biopolymer, enable high throughput screening useful in molecular electronic biosensor and spintronics. So that's all. This one is my research interest. So I'm interested in DNA and RNA for biosensor, membrane filtration, polymer solar cell, and muonium site and hyperfine interaction. And the newest project I'm involved is in anti-cancer molecule. So we are trying to working on that. Okay, I think that's all for me. So I would like to acknowledge everybody that helped me during my journey of research. That's all for me. Thank you.
So thank you very much, Dr. Wan. So any questions?
Thank you for showing the results. I have a comment about the graph neural network. And there is a good open source software for atomic structure with using graph neural networks. There are several packages. So one is NEQUIP, which was developed by the Harvard group in US. And also there is another NEQUIP, N-E-Q-U-I-P, NEQUIP. And also there is another graph neural network based software is a MACE, M-A-C-E.
Okay.
Yeah, there are several packages. So first you can use these kind of things and you can use the LAMPS. LAMPS is a MD software. So you can combine this graph neural network based potential and MD. So it is better to use this.
Okay, thank you so much for the suggestion. Maybe I will try and refer to you. How can I proceed? Will. Thank you.
Okay.
Any more questions? Actually, I have one. So I know a little bit about the DFT. So I'm just wonder how you define the hydrogen bonding in your simulation.
Which part hydrogen bonding? You mean for the
Yeah, because
MCI?
you have the simulation that define three.
This one?
Yes.
This one, because I use this method, non-covalent interaction method. You need to do by using Gaussian system software. You need to put, I think, certain keyword that will plot you the NCI detail, and then
Because
from that.
actually it's not really say that is a hydrogen bonding. So you have to make the definition.
Oh
as
no no
far I
oh no no.
understand.
I didn't make any definition.
Uh-huh.
It's directly from the calculation.
So it just tell you that already
Yeah.
hydrogen bond.
It
So
tell
you
me.
just use the value that you get from here, like the
Yeah, because from the calculation, and then we do the NCI plot, we get this value, and from this, we use the data to make the isosurface, and then they will show you where there's a hydrogen bond.
Okay, thank you. So any more questions? Oh yeah. The microphone.
Thank you for your night talks. I just want to know about the using the Gaussian, how to apply the muon in the Gaussian.
Okay. I will show you one photo. So here, where you have the system, you have your own system, and then muon is actually similar to hydrogen. So you can put hydrogen atom there, but you need to change the mass. The mass of the hydrogen and muonium is different. So you change the mass to perform the calculation, and then you can get the. It's different from I think different from molecular dynamic. I think molecular dynamic is more sensitive. Maybe that's why we cannot actually just put hydrogen and then run MD simulations to say that that is muon. That is yeah. But for DFT, you can do that way because it's not really affected. It will give you the result.
Thank you so much.
Thank you so much for your nice talk. I'm just a bit curious about the basis set that you use. Have you I saw you benchmark the Popo basis set, right? Have you ever used like other like families of the basis set, like the Dunning basis set?
Currently, no. This is only the data that I have for now.
Oh, okay.
Yeah, yeah. Maybe in other time I will try to do it with other family of pesticide. Yeah.
Okay. That's it. Thank you.
Okay. Thank you so much for the question.
Okay. So more questions? So if not, then let's thank the speaker again. Now we will move to the next talk. Okay, so the next talk will be given by Ms. Susanna Haya. Yes, the topic is molecular dynamic simulation to probe DNA muon interaction, single-strand DNA oligomer simulation. So, yeah, please start.
Okay, thank you to the chairperson. So, thank you to Dr. Watanabe for inviting me. And currently, this project is the collaboration between the RIKEN, University of Malaya, and also UKM, Dr. Fadila, and Prof. Violet. So in University of Malaya, I'm under Department of Chemistry and Center of Excellence of Quantum Information Science and Technology, and also affiliate with the industry relation on the mold design and Kubrios. Okay, so for today, I would like to talk about the single-strand DNA oligomer simulation. So before that, okay, so before we begin, there's ammonium is a like hydrogen isotope where there is the property of the ammonium is the 1/9 the mass of the hydrogen, where the ionization energy would be 0.9956. Okay, so these muons are unstable with the lifetime of 2.2 microsecond where before they decay into other particle. So these are the muon will be the muon negative, muon positive, and the ammonium will be the mu negative and electronegative, and muonite will be mu positive and electronegative. Electronegative. So from my research is go to the one interaction with single-strand DNA, where we already know that the double-stranded DNA is the very stable DNA, where we in here they share the genetic sequence to others, and for the single-strand DNA, this one is just a single strand with a phosphate and sugar, and also the nucleotide of the thymine, adenine, cytosine, and also guanine. So in my project, we will use the 12-mer single strand guanine. We choose guanine because they have the high affinity in order to trap the charge transfer. Okay, so these are the molecular representation of the single strand, the guanine nucleotide. So for this one, they have a phosphate, sugar, and also the base. So for the base one, these are the numbering that they use in order to determine the where the place to bind the muon. So okay, we will do the molecular dynamic simulation. So as you know, molecular dynamic simulation is like a movie where you can find the conformation of the molecule over the time. Where in here you can check all the stability and also much more property from the molecular dynamic that you want to study. So in here, we use the potential energy, where we focus on the bond stretching, angle bending, torsion, rotational, van der Waals interaction, and also the column interaction. So for our study, we'll use this molecular simulation to simulate the single strand guanine in water and also in vacuum. where we use the temperature of 300 Kelvin and also for the 500 nanosecond molecular dynamic simulation. So in here, we can see that the energy for the 12-mer single strand guanine in water is much more lower than all the others. Then this density also is the highest between the others. And then for the root mean square deviation, in here we calculate the movement of the molecule compared to the starting or initial structure for all the system. So in here we can see that the single strand guanine in water have the lowest RMSD value, where we can say that is the most stable simulation compared to the 12-mer single strand guanine in water. The black one you can see is much more fluctuate. This due to the flexibility of the single strand guanine, where when we simulate it, because the single strand guanine is not stable, then they will the phosphate group and the sugar will more likely to bind to the water. Okay, for the in vacuum, you can see the red and the green one is because there's no other things in the system. They only the strand, so there is no interaction between the others. It's only the vacuum, so it's will the result show you the straight line. So this one is the snapshot of the simulation, where we go for the 0 nanosecond to the 500 nanosecond. So it starts from the linear single strand guanine. So as it's come to the 500, it will is rotate to the where the phosphate group go to the water, and the guanine go inside to go inside the become a like a hill. So that is the energy distribution. Where from the last 100 nanosecond, I do the I pick all the energy, total energy. Then I plot it as the histogram, and from here we can see that the most common energy would be to at the negative 186,000 kilocal per mole. So for that one, so these are the random structure that I pick at the energy distribution curve, where the structure is moving, and also not it's like the phosphate is in outside, and then the nucleotide is inside. So they more likely, then phosphate more likely to go to the water, and the interaction between the water and also the nucleotide is quite small. Okay, so this one in the vacuum, for vacuum is much more linear because there's no other interaction between it. So the energy would be like this. Even in vacuum, before this we saw it is a linear one, but actually there is some movement inside the simulation system. So this one for the 6-mer, same goes to the 6-mer, but this one is less energy compared to the higher energy compared to the 12-mer guanine. So okay, this one is in vacuum. Same is linear before when we see it is linear, and then when we do the energy distribution for the last 100 nanosecond, it become move and become together. So in here actually, so next we go for the radial distribution where we calculate for the last 100 nanosecond. So for radial distribution function, we calculate from the reference atom to the circle outside the to the another from the initial atom to the reference atom, where in here we can see that the most interacting to the water with is the atom number 5, 6, and 4 for all the simulation. So, but based on the literature review from Dr. Fadila, they said that the muon will interact at the C8. And also from the Ian McKenzie, they also for the guanine nucleotide, they also said it will go for the number C8. So and then for from another reference for the ab initio calculation of DNA basis set using the 631 plus G star basis set. So from here, they study the DFT and the value of the basis set is over there. So in this study, they said that the number N7 is much more attracted to interact with others or with the other atom. So from here we can see the RDF for the first layer P1 and second layer P2, where in guanine is guanine N7 is the highest value for it. Okay, so next for the conclusion, like simulating single strand DNA oligomer water interaction serve as a stepping stone toward more complex system involving muon, where we need to have an accurate phosphate parameter like or using the ab initio MDIS for the muon interaction. So as you can see in here in the nucleotide guanine, we can see here that from the reference, the more likely atom to attach would be the number 7 and 8. And for my case, from my simulation, there we go for the number 4 and number 5 and also number 6. So in here we can conclude that the muon or other ion can interact in many places in order to get it can interact in many places in order to have the energy. They can interact in the many places. So in order to validate this simulation, I would like to investigate more to add the muon, which currently we are not successfully to parameterize it, and we need to have some parameter, or maybe we can use a path integral method or machine learning in order to get it more faster. After we had the parameterization, then we do the machine learning in order to fasten the simulation. So yeah, that's Oh, thank you.
Thank you very much, Rusana, for the very nice talk. So any questions from the audience? Maybe I have one. I'm just saw that you are focused on the single strand DNA. Why you should that from beginning, since this form is not the normal form in cells?
Because due to its flexibility to attract the ion or any other atom.
Yeah, but in the experiment, how can you do that? So you have to break the strand of the DNA before to do the experiment, or
Yeah.
and so what is the applications further that you would like to do with
We
this single DNA,
actually
single strand DNA?
we will study the DNA interacting with muon for the electron transfer. Yeah, sure.
Actually, yeah, correct. Yes, DNA is a double strand. Yeah, but many application on sensor using the aptamer. Yeah, and then usually it's become synthetic sequence, and then you can do application. But we just want to check on the base interaction and then see how interact with the muon with the smallest system. The system also theoretical. Guanin's 12-mer is not like the reality yet. Yeah, so this is only the startings on the small works. 3 months. So hopefully with more accurate method like ab initio MD, we can do the better sequence and then with the better methods. Yeah. So right now is have to link with the information from the lab on the how we can use muon for check the interaction site, the trapping site, how we want to use the muon for the new characterization of materials. Yeah, like defects or what. Yeah, Yes, we can synthesis the single strand any aptamer model. Sometimes it's actually this one is related similar to the aptamer model. They will have like hairpin structure after you do the single strand. Is follow the realities. When you have the single strand, it's become this hairpin structure to bind with different protein, different things. Yeah. So it's correspond to the experiment, but different series. Yeah.
So thank you very much for very clear explanation. Yeah. So any questions more from the audience?
So thank you so much for hi Rosanna. So thank you so much for your really nice talk. I just have a really small question about the interaction sites that you presented in the last part. So you say that each each study reports like different variable interaction sites, right? Can you give us some opinions of which one would you think that is going to be like the most variable sites based on your opinion?
So from here, from the studies, they confirm that the 7 and 8 also, is the best part, the best from what they had. So actually, for the muon is the like for electron positive, right? So I think for it can also bind at the end, because N also is the negative. So we can try we can try to validate whether it's can be bind to that atom or yes. So you have that
for the discussion in the future, because I think this one kind of like very simple, right? But it's, show you how we can do things with the molecular dynamics. And when you see the binding is many position that can bind. The arrow is the one that we think is the most probable size. Maybe you can point out the C8. C8 position is the one that we did, Dr. One did before with the DFT. C8, you look at the single strand DNA, this one C8. No, this the last one. C8 and then over. Okay, over the main structure and backbone where is a C8. This one C8 in the backbone structure. C8, you see the C8, right? C8, that one is our observation with the DFT. Where is the this part? This part is guanine, and then that one is connected to the sugar and the phosphate to the whole things. Then this part is the one that is a kind of stacking base, right? So we have the CS in the inside, and then N is the other people reference where is supposed to be negative charge. And then you think that move on positive charge would bind to the negative charge on the nitrogen. Then our result is showing for the densities, radiant probabilities, RDF for the water. The water is like kind of like heavy, more than the H plus, and then the charge different, and then the move on. But it's come because I will think only that the size and the charge different. It's come to the C5 and C6 and C4, which is kind of inner. To me, the whole things, it will relate to the structure and it will trap to the part that is kind of like inside the chain. So this one, what I think only, then this is from our observation. It's not like going to the outside part, even though like NH2, NH got the negative charge. And then if you have protons or that, it won't be trapped there, but it will be inside the main chain. That's what I thinking. Yeah. So how we could observe that position in the lab, I have to ask Dr. Isao.
Sorry, can I have one comment? Can I have one comment? For instance, this one is a simplest molecule. That is why I asked Rosanna to do the little bit the complicated one. Is she stayed only 6 months and start from the beginning. So in a short time, I asked her to do our ERS sample. But however, if you are interested in just simply try to simulate this single molecule by MD, then attach the muon somewhere and see the time dependence of hyperfine interaction. How the hyperfine field is changing in time, then it checks the distribution, whether you can reproduce the experimental value or not. So that is very important as a first step. But unfortunately, Rosanna had not done such kind of thing. Then if somebody is interested in, it's very simple. But mu is included. That means you have to think about the binding energy and also spin constant of the mu and molecule. But this molecule is simplest. So whether we can reproduce such kind of simplest model or not, the first step. If somebody interested in, please write. Then we can determine the spin constant by mu. Then we can apply to anything.
Okay, so thank you very much. So any more questions? So if not, that let's thank Lusana again. Okay, so now we move to another talk. I think now the talk will be a switch from DNA to batteries. Yeah, now it's a series of batteries.
Yeah, nice talk. So you say that this scan functional is the best one for the for this electronic structure, right? But is it also, I mean, have you ever checked, I mean, have you ever studied the dependence on the MUSR? Like, you know, you sort of showed us that this USR spectrum is in good agreement with your method, and does that depend on your on the functionals or yeah?
Okay, first I would like to clarify something. So my study in here, we don't use a scan per se because it's a very old study of mine. I use DFT plus U, so GGA plus U. In this case, we can derive a parameter that like this one, the U value, because we can just simply adjust the U value and try to find the best correlation with the experimental MSR data. But if you ask about the scans dependency on the MSR study, I believe it's also similar because this one on the left one is the first application on the scans functional on the similar material that I mentioned before on the lanthanum 2-4. And they also produce, actually they can derive the U value from the scans functional in here. And they also obtain like a very similar amount of U value that I mentioned before. So here I believe they got like around 4.88. And I also get around nearly 5 electron volt. So I believe even though the difference only on the functional, but if you want to try to apply a scans functional on the MUSR comparison, it's also feasible, I think, to do. But if you ask about the dependency, I'm not sure, but it should be very close to our results.
Okay.
Thank you very much. So any more questions?
Thank you so much for your insightful presentation. So just a quick question about the how you simulate your system. So you're mentioning that you are using machine learning with the app initial molecular dynamic simulation, right? Can you tell me a little bit about how you set up your machine learning MD simulation?
Okay, that's also what I want to ask to the expert. The problem is I use the commercial based on the package, which means they already incorporated some specific machine learning approach to their software. I believe it's called a machine learning force field theory, but I'm not really familiar with how they can do that and try to. I also just this lunch on the coffee break session I already discussed with Professor Shiga and also Professor Naga. I really want to ask their opinion. Whether my calculation is correct or not. That's the problem. Even though it seems to be very close to the experimental data, because I'm not familiar with the machine learning itself, I need to make sure first that our results is correct before I try to write some papers, right? So this kind of meeting is very needed for me to understand fully, understand what can we do with this machine learning technology. So.
Thank you so much. But and also congratulations in advance for your very accurate results. And hopefully your method is like valid. Yeah, thank you so much.
So any more questions? So if not, let's thank the speaker again. Okay. So now we move further to the talk also about the batteries. And yeah, I think that for the energy is application.
Okay.
Can we see?
The slide in the Zoom. Okay. Desktop two.
Because during the talk, we get complaint about the sound. I do not want to get complaint about the screen again. So we have to check first before we start. So now we are ready to start with the second talk will be given by Dr. Erwan Ramri. I hope I say it right. So then he can introduce the title of his talk by himself. So let's start.
Okay, thank you, Chairman. My name is Irwan Ramli. I came from Department of Physics, Chokro Aminoto Palopo University. My talk today will be study dynamic of lithium ion in battery material by DFT with the implementation machine learning in IMD, App Initio Molecular Dynamics. This job was done with collaboration with Watanabe-san, Dr. Fadila, Dr. Redo, and Ohisi-san from Cross. First, I would like to show you where I come from. I came from Indonesia, but not Jakarta or Bandung. I came from the center of Indonesia, the island of like K. Luckily, there is a flight from Chiang Mai to Kuala Lumpur and Kuala Lumpur direct flight to Makassar. This is my place. Okay, what we do in Palopo is computational research. Luckily, we have a strong collaboration with the Watanabe-san. We can easily access supercomputer in RIKEN, and we can enjoy research in Palopo. Even though in very rural area, we can still enjoy research with the supercomputing system in RIKEN. What we study at this moment is about battery materials. The performance of battery is defined by key parameters. We call is diffusion lithium ion diffusion coefficient, DLI. And this is determine the performance of battery and so on. But how we measure DLI? There are several techniques, but the result is very scattered. The result from experimental is very scattered, and we can see here MSR result is the scatter is smallest one. And this is the MSR results. And if we summarize, there is a two technique we call macroscopic and microscopic. And MSR, they provide unique time window and most range, and this is very suitable to the sense the jump of the lithium ion motion. And how muon sense the motion of the lithium ion? In the MSR, we send muon into the system. If there is a motion of lithium, there will be fluctuation rate of the muon that we sense by the spectrometers. And this equation is directly correspond between fluctuation rate of muon and the lithium ion coefficients. This is the typical results that's shown by Watanabe-san this morning. This is the first result. They demonstrate how we can understand, how we can measure DLI by using MSR technique. But there is two fundamental programs in this experimental setup. First, we don't know where is the muon inside the system. And the second one, we don't know whether muon sitting in one position or move around inside the system. This is the two fundamental problems. Actually, we have already answered this question in the superconductor system in LCO, just Dr. Ramadan recent before. Where is muon inside the system? We can see muon, because we assume muon has positive charge, it will go to the most negative potential inside the system. And the second one is muon located in the fixed position. here this quantum behavior of the muon. We call it 0-point vibration muon. Even though in the lowest energy in the ground state, muon still have position. Muon still have energy. Due to this energy, muon is probably moved from hopping or from one position to another position. This is already demonstrated, and how we can include this effect in the LCO case. And this is our publication in 3 years ago. But this is never been considered in the measurement of the DLI coefficients. And we can, at this research, we try to include these two effects into the analyzed MSR results on measurement of DLI coefficients. And this is, we start our strategy. We start with the two common system, lithium cobalt and lithium ferrum phosphate. We calculate the lattice parameter in the 0 Kelvin. And from this, we can choose which functional is suitable for our system. That's Ramadan San demonstrate in the previous talk. And the effect charge and discharge on the crystal parameter. Then calculate the trapping potential of muon, and we can clarify whether muon sitting or not inside the system. And if the temperature are above 0 Kelvin, we can do by IMD. Okay, first one, there are many functional available on FAST. Many functional, each version come with a new functional. And this is the functional we try. And first, we try with which functional gave us the lowest energy. That's the assumption, because this is the DFT in the 0 Kelvin. We choose the lowest energy. This is the lattice parameter in 0 Kelvin as a function of the lithium content. So on. And this is the, where is the muon? To determine where is the muon, we calculate the potential map in the system, and we choose the most minimum potential, and we put muon in that position. And how we model, how we put muon inside the system. This is the functional, this is the hydrogen element provided by FAST. We model muon as a hydrogen with the lowest electron valence. This is the 0.25% valence in the functional. We choose this one because this one is closest one to the muon system. Sorry, to muon properties. We put muon in the, because in the previous calculation, we already find the minimum potential. We put muon in that position. At muon, we send, in continuous muon, we send muon one by one. It means muon is ultra dilute impurity. Then we must have large enough supercell to simulate the realistic condition. And we try in the unit cell. You can see here there is a change of the unit cell. That means muon, this unit cell is not good enough to simulate realistic condition of the muon. We go further with the 1 to 2. Still we can see some change of the supercell. And if we go to 2 by 4, it's almost no change in the volume of the supercell. That means the periodicity of the muon can be neglected in this unit cell. So in this supercell, and we put muon in that position and do calculation and relax the system, and we can see change the position of the muon. This if we see the detail potential inside the muon, we can easily in which direction muon or lithium is moved. And this is the previous results by some Chinese researcher, some Chinese group. This is the lithium path motion. Okay, this in which we come to the next question: in which position muon is probable to diffuse? We slice in one A direction, B direction, and C direction. This is the slice of the B direction. The potential trapping depth is around 0.8 electron volt, and this is the B direction, and this is the C direction. And from these results, we can see the potential trapping of muon is comparable to the potential trapping of lithium in the previous results. That's from this result, we can assume muon is not sitting in one position, but diffused together with the lithium in the measurements of MSR. And how we can verify our assumption? We go to the F initio molecular dynamics, and this is the morning talk. F initio molecular dynamics is computed on the fly from the electron structure calculation usually DFT. And how it works? We solve Schrodinger equation for the electron, compute force on nuclei, and integrate Newton's equation of motion, and so on. This is done by FAST. Okay, sorry, we are not expert in the machine learning. We simply use FAST implementation machine learning in FAST. We need, because muon is ultra dilute impurity, we need large system. This is the system we need to simulate by using IMD. It's contain 897 atoms, and lattice parameter is around 20 Armstrong until 25 Armstrong. This is a very large system we need to simulate by using IMD. Luckily, we have PASS and Hokusai, this system in RIKEN, and this system have two system. We call it BW large massive parallel computing, MPC, and LMC, large memory computing. When we try in the massive parallel computing, it's out of memory because our system is very large. It's out of memory because in the massive parallel computing, the default amount at memory per core is only 1 gigabyte. And in the large memory computing server, we have per core amount of memory is 30 gigabytes. And we try do a large memory system. If we use large memory system, we can only simulate 10 steps. From the MD point of view, 10 steps is very small. And we go further. Sorry. Then we use machine learning implementation and PASS. So where is my slide on machine learning? This one. Machine learning is, we use machine learning force field. This is in order to achieve DFT level accuracy while maintaining efficiency and scalability of the MD simulation. From this when we apply this machine learning, we can simulate until 380 steps with the time step 1.2 femtosecond. And we can simulate until 72 femtosecond. And we can see here there is a motion part of the muon like this. And it distorts, there is a local distortion of the muon inside the system. This is our first results. But we come to the problem because Hokusai, our problem at this moment, only allocated two nodes allocated for each project number for the large memory computing system. And this now for this fiscal year, our allocated time is already used. True, for the large memory computing. Me. Because it's very limited. It's very limited. No, not so much. I just got email yesterday. The email yesterday. sorry, this due to the our limitation, but luckily we have 4 project number in Hokusai, right? 4 project number. Maybe I will ask for permission to the Padilla-san, Ramanan-san. Please give me your allocated time to me. Okay, due to this limitation, at this moment we can show this result at this moment, the implementation more machine learning in the DFT calculation. And the summary, we demonstrate how crystal structure changed by charge and discharge. And the most important things is the dynamic of muon might contribute to the fluctuation rate of the MSRC spectra, which directly correspond to the DLI. This has never been considered in the previous analysis of the MSR measurement in the battery materials. And detail ab initio molecular dynamic in order to understand the mobility muon in the battery materials. We need a longer time step in the system. Thank you.
So thank you very much, Dr. Awan. Awan, I'm not sure that I say it correctly, for the very nice talk. So any questions from the audience?
I have a comment about the machine learning case. Usually, if I use machine learning potential, first we consider the small systems. I think the 800 atom is too large, so you have no resources. Okay, so I mean that, for example, if you consider some kind of 200 atoms, then you can train with use of BASP. Then you increase the size of the system. Then you can do the larger system. So first, I think you have to try the smaller system to train the machine learning potential with BASP. I think it is better. Maybe, yeah. 800 is too huge, I think. Yeah. And the number of training data is very important. So, and I think the 300 is not so many. So please reduce the size and to increase the number of the training data. It's better. Yeah, this is a comment.
Okay, so other questions? Yes.
All right, thank you so much for your presentation. I agree with Nagagi-san about the simulation setup. It's really huge for ab initio MD simulation. So I think if we can find a way to reduce the size, it would be much feasible to simulate it. And I have the same experience as you when I use Hokusai, but I almost maxed out within like 3 months. So yeah. But I have one question about the muon trapping when you are probing the lithium diffusion, right? So you mentioned that lithium the muon diffusion is the movement of the muon inside the cell is behaving accordingly to the lithium diffusion path, right? So do you have any plan or ideas of how are you going to incorporate the muon encampment inside the lithium path?
Oh, sorry. Thank you very much for the questions. This is the fully charged of the lithium ferrum phosphate. This is the sorry. Okay, this is the previous results from other publication. The potential barrier of the lithium ion motion is around 0.73 electron volt. This is from the previous other researchers, other reports, and from our calculation, the potential trap of the muon is comparable to these results. That's why we assume muon will diffuse together with the lithium inside the system. But how to clarify? We start our calculation with this is the fully charged, and further calculation we need to try in the how about the 0.5 lithium content inside the system. Okay, please understand this is sorry, this is the first step of our calculation. Thank you.
Thank you so much.
Maybe not. So then let's thank the speaker. I think we have 2 more talks. Maybe we have a little bit break. Maybe people want to go to toilet or walk a little bit. I think we can have 5 minutes for break. But I would ask the speaker to come to connect the computer. Then we see in 5 minutes. Yeah, we will continue at 3:45, but in the meantime, I will ask the speaker to connect the computer and prepare for that.
ปิดอันนี้หรือเปล่าปิดใน
ก็ลองเทสดูนะ
Okay, I just would like to make a test. This is okay. Now it's good. Now it's good. Now it's good. Yeah. Wait. Okay, so now we can continue. Thank you. I would ask Professor to start from beginning, I think, because all the audience on Zoom lost from beginning already. So we will restart again this talk.
Yeah, thank you very much.
Okay, yeah, please start.
Okay, yeah. So let me start at the beginning. And thank you very much for this opportunity and Professor Watanabe for kindly inviting me to join in this seminar. This is my first experience to present in front of you in the computer scientist community. So my research collaborate with Indonesian guy who now working in Waseda University. I already published this in the last year, and okay, yeah, already published last year, and so this part of a small part of our publication, and already know that okay, yeah, already know that in lithium-ion battery, interaction between lithium and the surrounding chemical compound is very important. So so this affect with the ion diffusion or physicochemical reaction of charge transfer ion or charge, and for intercalation process into the active materials. So this collectively determined with the battery performance, like stability, life cycle of efficiency or something like that. So therefore, I want to join hybrid approach between experimental investigation and the computer simulation to gain deeper understanding about what the mechanism interaction between the lithium and the molecular polymer